Yes. You're supposed to hear me. Are you hearing it? Are you hearing? Yeah. That should be fine, I think. Hmm? Hmm? Your name is on the live stream. Yeah, it's fine. Otherwise, so let's keep it. No. Instead of Safari webcam, here's its name is. It's fine, I think. But then he needs to say himself as Safari webcam or something. And then, yeah, it's fine. The video is fine. Video is fine. I'm audible. Everything is fine. Can you hear me? Okay. So I'm putting this over there for the question.
Hello.
We good? We're good, right? Rakesh? Should we start? Okay, so hello everyone. Let's get started for the session. I hope you all had good lunch and not sleepy yet. Okay, so let's get started. So on behalf, so I'm Rahul. I'm a recently graduated PhD student from Safari Research Group working with Professor Onur Mutlu. So on behalf of my other co-organizers, Konstantinos, who is unfortunately not here, and Professor Mutlu is standing back in there. I welcome you all to the 4th Data Prefetching Championship. It's been quite a while. We had this in the community, so let's get started. Okay, so first thing first, why do we even care about prefetching? It's something that has been developed since last 50 years, and is it still relevant? So just to answer this, I would put this slide over there. So this is the ARM Neoverse V2 presentation from Hot Chips 2023. So what is shown over here is that from the previous generation Neoverse V1, it achieves a 13% performance speed up on top of V1 in SpecInt, and nearly 40% of that, 13%. So 5.3% is actually coming from one single feature, which is the hardware prefetcher. So that kind of sets the tone that prefetching is still important and living well for providing the performance benefit of high performance processors. So why do we need another DPC? Because it's been a while. We used to have these championships, let's say once in 4 years, and it's been almost 7 years that we are having another iteration. So lots of things have changed since then. Most importantly, workloads have changed significantly. So we are seeing emergence of AI ML inference, CPU-based inference, data center class workloads, complex graph-based applications, as well as the data footprint of these workloads are increasing tremendously. And on top of this, we are also seeing emergence of 32 core or more core processors embedded in one socket that essentially puts a lot of pressure in per core main memory bandwidth available to them. So with these trends in mind, the goal of us for this DPC4 is to evaluate new innovative ideas on prefetching under a common evaluation framework to tangibly improve the state of the art in prefetching. So this is what it's going to be the format of this championship. We used ChampSim as the infrastructure to evaluate all the ideas. Participants are free to evaluate prefetchers at any cache level, L1, L2, LLC. The only limitation that we had is a hardware budget, so which is mentioned over here, but we have not enforced any limitations in the complexity because it's more subjective. But we have also enabled the participants to access a wide range of system level feedback to enable dynamic adaptation of their prefetching algorithm like prefetcher accuracy, main memory bandwidth usage, rolling window IPC, and many more. So few new things that DPC4 is introducing for new workloads that are representative of our time. For example, state-of-the-art AI ML inference that are CPU-based, optimized with CPU-based libraries. Like for example, Llama 2, visual transformers, Whisper, and many more. And then we are also going to release a wide range of workloads from Google's warehouse-scale computers. So this has been released in the past in a different format, but then thanks to our collaborators also in Google, so they have agreed to release these traces, which I believe that it's going to be useful for the community in the future. And then also many more graph mining workloads, and there are other workloads also in the pipeline. So maybe at some point we would also release them. And then we have enforced a broader evaluation across the board. So every submission was evaluated in 3 configurations: single core with ample DRAM bandwidth, limited main memory bandwidth, as well as 4-core random mixes. And then we have enabled, like I said, multiple dynamic system level feedback to the computers to make use of these information as they seem fit to dynamically adapt their prefetching algorithms. So here are some key numbers of DPC4 at a glance. So we are going to see 8 competing ideas in today's session. So each of these ideas have been evaluated across 610 single core workloads, both in limited bandwidth as well as full bandwidth, and 484 4-core workload mixes. In total, they consume more than 3 TB of space. We are going to release everything. And the evaluation took a heavy toll. It's easily for more than 50,000 CPU core hour we have spent in this. And thanks to our PC reviewers, we had 9 PC members who have provided at least 3 reviews to each of the submissions to vet it. And yeah, so that's what the DPC4 scale. I should mention this, that this is the first for DPC to work in this scale at least. So the question is that did we meet the goal? The answer is yes. So this is what the performance chart looks like. So on the x-axis, you have different scores. The higher the score is, the better. So this is what the baseline is. Everything is normalized to the baseline, and baseline means that we already have Berti at L1, P3 at L2, which already provides 15% performance uplift over no prefetching. So given that as a baseline, we are seeing this as the competitor of the winner. So that's 5.2% performance in single core across 600 plus traces, 2.6% improvement in limited bandwidth, and 2.8% performance in multi-core mixes. So this number might look small, but given the scale of the evaluation, I think this would have tangible impact going into the future. And if you look into the full bandwidth number a bit more, then we are seeing actually different workload categories are getting improved in different scale. So AIML, given the streaming access pattern, that improves a lot, almost around 27% improvement. Graph spec, we are seeing a healthy improvement. Google workloads, as a specific matter of fact, we are not yet seeing good improvement. So that essentially shows that we have multiple opportunities in the future. So that's something to keep an eye on. Okay, so with that said, so this is going to be today's agenda. We would have two talks from the industry veterans. Leeor is over there, so he's going to have the first talk. And then we will also have a talk from Akanksha from Google. She is a person who worked with us on getting the Google traces out, so thanks to her. And then we are also going to see competitors, 8 competitors talk, and in the end, we are going to go through the results and announce the winners. So this is the today's agenda. That's we are having it in 2 sessions. We would have 4 invited, like 4 papers and with 1 invited talk in each session. And yeah, so that's kind of everything from my end. So welcome everyone again for the championship, and I would hope that you would have a good time and new ideas to discuss. Thank you very much. One second. So let me just introduce Leeor here. One sec. Okay, so the first item on our agenda is for the invited talk from Dr. Leeor Peled. So Leeor has received his PhD from Technion under Professor Uri Weiser and Yoav Etzion, focused on ML-based prefetcher implementations with rich context. He spent over 22 years doing what? Am I not sure? Just give me one sec. Okay. These things always takes time to adjust. Let me see. You see it now? Okay. Hopefully I did it correctly this time. Okay, so where was I? I was introducing Leeor. So he spent over 22 years doing CPU core architecture research, starting at Intel Haifa, working on various core clusters from Sandy Bridge, Ivy Bridge, and Skylake until Golden Cove and Lion Cove. He then moved to Huawei, working on CPU cores for mobile phones, server CPUs, and many other domains. So currently, he is leading the Huawei CPU architecture research with a great teams that spans across multiple sites: Israel, Zurich, Cambridge, Edinburgh, and China. His main focus is on predictors, parallelism, caches, hardware software co-design, system OS co-design, dynamic optimizations, compiler, but he may be willing to talk about many other things given a chance. So it's my pleasure to welcome Leeor. Yeah, the stage is yours.
Thank you very much. So thank you very much. Thanks for inviting me. I would say it came as a surprise, but then I wouldn't be a good prefetcher guy, right? And let's just say, okay, never mind, I'll match. So okay, let's talk about prefetching a bit. So in the interest of time, are we seeing that? Ah, I'll use this instead. No, this doesn't work as well. Okay, you can skip this slide. Oh no, I skipped instead. Okay, so Rahul already introduced me, so thank you again for inviting me. I will say a word about Huawei, my employer, because this championship is also partially sponsored by them. So fairly large company, I think, slightly twice bigger than Intel that I worked in for a long time, working about many things. But the interesting thing is that we're working on these CPUs. So pretty much all the concepts you're hearing about in prefetching now goes into our CPU, which in turn goes to mobile phones, servers, and cars, automotive industry, data base stations, and so on. So that's a very nice chance to work on actual products. And I encourage all of you who are pursuing microarchitecture, I wish for you to work on things that will eventually go to the entire world. Because with Intel, for example, I know that most of your laptops here has a little bit piece of me inside them, which is something really fun to think of. I mean, legally, every presentation about prefetchers has to start with a memory wall, right? We're bound by laws. So obviously, we are going to mention this. So the interesting part, we've all heard about this quite a few times. The interesting part here is that the memory wall that we all know from the basic textbooks, right? The CPU memory wall is still a problem, but it actually becomes a bigger problem in the era of AI, right? Wherein we have the middle graph is an exponential graph that still grows exponentially, which is pretty cool. The reason, by the way, is that the CPU graph that we know from Hennessy and Pearson was showing performance of CPUs, right? So that was the consumer of memory footprint or memory bandwidth. But in the middle graph for AI, it's actually the consumption of memory models, of the models that we want to run on these CPUs. So it's the consumer of the consumer, right? Where we don't even need that requirement in terms of compute power, let alone in memory bandwidth. So this is still going to grow, and the memory wall keeps getting bigger and bigger. So how do we deal with that? We prefetch. Okay, that's a fairly simple problem. We have been exploring prefetchers for, let's say, how long? 50, 60 years probably. Usually someone comes up and says, no, it's actually 80 years. We've been discussing prefetchers still when we had mechanical computers. I don't know. So this is a cute experiment. I looked up in Google Scholar how many papers about prefetching per year. So the absolute numbers don't really mean anything because Google sometimes give you citations and so on. So that's not the matter. What matters here is the trend. So the trend shows that we are still publishing more and more prefetching papers. So obviously this is still an open problem, right? There's still something left to research. On the right side, you see a nice breakdown that was done by Sam Ainsworth, I think, which shows how many different topics or subtopics you have in prefetching. And this only goes and expands even further. So I don't know if there's any updated version of this, but this is already pretty impressive, right? So there probably has to be something left to explore, right? So this is the question, right, that should matter to all of us, especially since we have so many students and academics still working on this, right? We were born too late to explore the oceans. I apologize, not much to explore there. Maybe a few things here and there. The maps keep changing, I don't know if you listen to the news. We're too young, too early to explore the galaxy, but we're just about the right time to invent perfect prefetcher, right? Because we have all the basic knowledge, everything we need to do, but is there something to discover? Right? Have there been any significant change in the domain of prefetchers in the past few years? And is there still something to do? And to put the question in a slightly different perspective, since we have Onur here, who raised the same question in his keynote in Micro, is it still possible to get a paper accepted in a conference about prefetching? Well, obviously, we have a few of them here in this conference, in HPCA, I mean, but it's becoming more and more difficult, as most of you probably know or will discover in the next few years. So why is that so difficult? So I don't want to go over all the history, right? Just very briefly, because everyone knows about the basics, right? So we've had spatial prefetching for a long time. We have next line that becoming sequential prefetchers, and then becoming stride prefetchers, and then we said, okay, strides can change, so let's take alternative strides and then signature-based strides to make it even more advanced. And then we started with temporal prefetching, right, which is a kind of a pivot. And we said, okay, we can correlate or associate addresses, but let's get even smarter. So we start by Markov prefetchers, and then it becomes history-based prefetchers, and so on. And then we start adding context, And there are a lot of papers about the storage costs of these things. And then we said, hey, why don't we just take these two domains and merge them, right? That always works in the academic world, right? You take two things and you glue them together and you get something new. So we have spatiotemporal prefetchers where you start associating or correlating patterns, spatial patterns, over the history, right? So you start looking at how things change in that concept. So we have recurring deltas and we have patterns and correlated patterns and so on. And then we're asking ourselves, what's the next step, right? So everyone keeps saying, okay, the next step is irregular patterns. So let's talk about irregular patterns for a second. And I'll tell you why I hate the term irregular pattern, because you cannot define something based on what it is not, right? It's irregular pattern. So basically we're saying, let's prefetch everything that is not regular. But what does it say? What does it even mean? We're okay?
Try and fix this.
What?
Hiding.
Oh, that's fine. If there's nothing important on the left side, I hope. Yeah, I apologize. I need to leave more margins. So irregular prefetches is a very bad name because it doesn't tell us why they're irregular, right? So, okay, let's see. We have some cases where you have pointer chasing. So that's a fairly simple use case in many workloads. You can advance to more advanced linked data structures, right? You have with multiple types or with diverging connectivities. And then you can also start asking yourselves, what are the algorithms that run on these things, right? So you don't just have the data structure, you have an actual algorithm that works on it. And then you have to ask yourself, what is the algorithm trying to do? If I'm descending a tree or walking a graph, what is the algorithm trying to achieve? Is it going to jump around from place to place? Is it going to take a certain path? Am I going to do something like a BFS where I kind of split in multiple directions at once? Or am I going to do a DFS, right? That's the simplest example, and it already differs and changes the access pattern dramatically. So these are very interesting questions that you can ask yourself, but it doesn't tell us how to prefetch these things exactly. In addition, you can say, I can have random walks. How do I predict these things, right? So that doesn't really answer the question, what are we going to do next? And so this pretty much leaves us with the question, again, that we started asking, is there something we can still explore? Is there something we can improve? And I want to take a stop here and say, what actually happens when we come to explore a new topic in science in general, right? Because we need to ask ourselves, what is the problem we're solving, right? Science is about solving a certain problem. So first of all, you need to identify the problem, right? Then you want to solve it. You give the best solution you have, someone else there gives a slightly better solution, and you optimize and you converge eventually to a very good solution, right? And then you come to an interesting point, which is the saturation point. Your solution is very good, the cumulative solution of the scientific community, and sometimes also the engineering community, the industry, right? Because you publish your prefetcher, someone in the industry is going to build it, right? And in our domain, industry and the academy work together hand in hand. So somebody in the industry might actually engineer your prefetcher a little bit better than you did, which is fair enough, okay? And we come to a point in time where we may actually have a solution that is too good, right? Where did that happen? I'll give an example. I don't want to talk about prefetchers in that context because it's a bad thing, right? So I'm trying to use this as a negative example. This is what happened with branch predictors. We can trash talk these guys, right? That's a different championship. They won't invite me. So with branch predictors, we have the Tage SEL, which is, everyone knows that's the best prefetcher out there. Nobody can beat that, right? Even if and they still do championships, and they still try to beat that, but this is, at this point, slightly a problem of engineering, right? You're trying to engineer something better. If someone comes up with a fundamentally different concept of how to do branch prediction, and also in our world, a fundamentally different prefetcher, he's going to have a really hard time to beat the best known method out there, right? The best known solution, because it's not engineered enough, right? He needs to work out all the tiny details. This is not something you can do with a single work in the academy, right? A student working on this for 1-2 years is probably not going to beat the best known method that has been specialized and optimized for many years now. So that's a very interesting challenge. And we need to remember that sometimes it's not about beating, especially when we're discussing championships. Sometimes it's not about beating the best in class. It's about coming up with something that is fundamentally interesting enough and has lucrative potential optimizations ahead of it. So that's something to consider. So we're in this cycle somewhere, right? And we have a bunch of problems. So we started by the very simple problem. We need to predict the next address. And we said, okay, let's come up with a function that tells us, given the last address, right? I don't know if you can see it. It's a little bit, I apologize for the font size. So given the last address, n minus 1, what is my next address? Okay, apply some function. And that function usually was a stride or some spatial aspect. We could optimize it a little bit further because that didn't really solve the problem. It gave me the next address, but I don't need the next address. I need to hide latency, right? So I want the address a few steps ahead of me. So fine, we can figure out how to optimize this if given a stride, the reasoning behind my function. But that also wasn't enough. So at some point, this has saturated, and we found out that most of our patterns, not most of them, this covers probably most of the patterns today, the spatial prefetches, but this is not enough. So we said, we need a better solution. We need to add some storage that tells us more on the problem, right? For example, context or things like that. So we said, we optimized a bit, we advanced the problem, and we had a better solution for that. And vice versa a few times. And that brought us to history-based spatial prefetches and so on. And then at some point we said, what if our workloads have multiple patterns, multiple different patterns? I need multiple functions. So that's fine. We added ensembles of prefetchers, and we engineered the problem even further to solve the original problem. And now we're asking ourselves, what's left? Okay, what do I have to still work on? So I'm not going to talk. I'm going to talk about this in a second. You reminded me. You mentioned the warehouse scale workloads. I think this comes from the paper that presented these workloads. So this is an interesting way. The color coding here, I don't know if you can see that, are different types of instructions, right? Arithmetic instructions, add, sub, things like that, multiply even. But some of the colors, I think the teal one, I don't know if the colors come out nice enough, are loads, right? Loads, and I forgot to mention, these circles for different workloads represent the breakdown of different sequences of instructions leading to the creation of an address, right? So if you want your address, you create your address, what is the, let's say, the slice or the code that leads to the creation of that address? What kind of instructions does it include? So obviously, simple strided patterns would come from cases like the first one, the pure orange. This is glib quantum, a very easily prefetchable workload, where you have sequences basically of adds that give you a sequential spatial stride. But what happens when you have loads, right? There's absolutely no way to predict with a spatial pattern something that comes from a derivation of a pointer, a dereference of a pointer, not let alone if you have multiple pointers. So some of these have multiple loads, right? So pointer chasing, but even before that, things like the jump pointers that we mentioned, right, earlier. Never mind. So what do you do with these kinds of patterns, right? They're not spatial patterns. You can learn them temporally, but that's cheating, right? You cannot learn the entire data set. What if it spans multiple millions of memory elements? So fixing the storage is not going to help, right? You need something else to solve this. So you need to redefine the problem. So one way is we can move from functions to compute, right? Instead of memorizing the correlation between addresses, you can learn the correlation between an address and the code that generates it. So this has been done to some extent. You have run-ahead prefetchers that basically try to execute the code, but they're not really finding the correlation between they just run ahead. I wouldn't say blindly. They run selectively the code that is relevant, but they don't really give you the answer. What is the meaning of the code, right? What is it trying to achieve? So this is a term we tried to coin back a few years ago called semantic prefetching, right? We're trying to use to detect the code that gives you the ability to generate the address and figure out when to run it and how and on which conditions. Another option, by the way, is to figure out better learning models. So we'll talk about this in a second, but another work we had was neural network-based prefetching, which is kind of trying to answer the question, okay, given the question of correlation, right? Given a certain pair of addresses, can you predict, can you create this correlation with better means? Not just learning them blindly on some table, but creating these correlations through other means, and neural networks were at the time a very important learning model. So we said, okay, let's give a neural network the chance to learn that. So that really didn't scale well, and we're still not there. There have been a few papers since, but this is still an open and lucrative topic, because there have been a lot of advances in neural network and the machine learning field. So let's try to discuss what's next with a few minutes I have left. What's left? So this is in no way exhaustive, right? There are a lot of other topics that may be left, but these are a few suggestions that I think might be interesting. So first of all, we have complex pattern, like we said. What exactly makes them so complex, right? Is it because, so just a few examples, you can have cases where you're trying to hash, so arithmetic operations, but it's very hard to predict because there is no clear spatial pattern, but there is a very clear sequence of operations that create the next address, right? So you can use that. You can do dereferencing, like I said, or you can combine these things. And the third bullet there is conditional address generation, right? What happens if the code that creates this address, it actually has branches inside or conditions? For example, MCF, you have a quick sort function, and you have to pick which side you're going to go down, right? In this, or if when you walk a tree, there's a condition you want to apply. How do we solve these things? Can we prefetch them? In a sense, it makes our prefetcher, it forces our prefetcher to also act as a branch predictor when you try to predict the path. And we know a lot about branch predictors. We just mentioned we have the best branch predictor in the world, right? Okay. Then the question becomes, okay, so we have a bunch of examples, but we need to generalize them because we can't just cover all the different examples. We need to figure out, can we find a generic rule that teaches us how to find these patterns, no matter what they are, right? Another topic is that we need to find better way to correlate, like we mentioned, right? So we need to use context to record only relevant correlations, right? Because we can see after a given address, when you look at the sequence of accesses, you see a lot of addresses, right? Which pairs, or more than pairs, right? Which combinations actually have meaning, have connections, and which are there just because they happen to be alongside each other, right? So we need to have better context to correlate these things, and we need to have better context to trigger them. And sometimes when there are several chains of sequences or several patterns, we need to find a way to disengage them, right? To dismantle them or to untangle them, right? Another interesting term, which is kind of halfway solved, is multi-level prefetching, right? So I think Berti is one of the best candidates there. How do you prefetch when you know that you have a cache hierarchy and you don't just want to prefetch, you also want to put this in the right cache level for a given duration or a given latency, right? So it's kind of a concentrated effort to bring the data at the right time to the right place. But for that, you have to prepare it at the right time, a different right time, at a different level. So we probably have this kind of solved optimally, maybe to 3 levels. But what happens when you have longer latency? How do you do this at rack scale, right? How do you do this with networking, through CXL or UBus, right? How do you do this with storage when you have to prefetch from disk? So these are completely different domains. They have their own workshops and conferences, and we need to learn how to work together. Another term is multicore, right? So we probably want to figure out how to solve multicore fairness. We have throttling mechanisms, but they're not smart enough to work in concentration. We need to have some sort of overseeing mechanism that sees all the different cores and kind of concentrates the efforts there, because otherwise, if you have a symmetric situation and you try to convince the prefetchers to work together, they're all going to you're going to get to an all or nothing situation, right? They're all going to prefetch or they're all going to throttle themselves. Another example is what you do with specialized workloads. This is a completely different topic I don't want to discuss, but I think you mentioned, well, for example, we need to start working on AI workloads. So you've added some. By the way, incidentally, there is a new spec. This is also going to have to be in the, so they didn't officially publish this, but I think last week they published a pre-release or something. So rumor has it that they're going to completely change spec from scratch, right? We also know the guy who worked with us at Intel. He did most of the benchmarks, and they completely changed everything. So that's also interesting for us now. But there are other domains that we need to prefetch. So ray tracing, for example, is a really interesting one. I don't know how many of you have heard the terms BVH trees or octa trees. So when you do 3D ray tracing, the objects are aligned as trees that represent their spatial, not like spatial prefetching, spatial 3D spatial alignment and connections. But when a ray shoots from one side of the screen to another, right, or through some angle in 3D space, it actually cuts through all the different trees in multiple levels, and it's very hard to know which ones. So a ray can hit this object, then another object, but they're not even closely adjacent. So you need to figure out how to do this as well in databases and so on. And now the last term, and I will finish with this, I think is ML-based prefetching. And we've discussed, the previous one was prefetching for ML, right? Which is also interesting, by the way. We used to think about ML computation as something that is very regular, right? They have matrix multiplication. That's easy. We don't need to, this is solved, right? This is mostly spatial. But no, in fact, ML workloads are becoming more and more complex these days. You have scheduling problems, you have tiling problems, you have all sorts of weird, interesting interactions. And this is and of course, reuse and attention-based models. So how do we learn these workloads, and how do we prefetch we design specialized prefetchers? But then the other direction is, how do we use ML to improve our prefetching, right? So we have a lot of techniques that we already started exploring. So some of the people in the room and some of the presentations today are going to talk about this. So we have reinforcement learning based on bandits. I think there's a paper today about this. We have reinforcement learning based on neural networks, based on table PTR, right? QL, I think. So we have a bunch of topics, a bunch of methods, but can we advance one step further? Can we actually generate these? Usually they choose actions, right? They choose which action to perform. Can we actually generate addresses from these things? If there is no apparent action, right? Can we generate an address from scratch? So we tried this at the bit level. That's very hard because they don't converge. It's not a convex problem. We tried that at using embedding. We try that using partial embedding, for example, offsets within a page, and then learning the page with embedding. So there has to be something else as well, right? So what is this other thing? And finally, can we also join the LLM wagon, right? LLMs are a completely different story. They learn a language. What are we trying to solve here? When you look at the prefetcher, it looks at the sequence of historical addresses. LLMs are perfectly adapted to parsing a long sequence of words in that sense, but words or our language comes as a memory trace. So can we send this input into an LLM and produce something sensible, right? Because they have attention, they have basically all the things we need to do as prefetcher designers are already covered. But how do we use this if all they produce is basically only available offline? We're not going to build an LLM on a CPU, right? Can we produce these patterns or these LLM trainings, right? Can we produce this offline and somehow learn something, extract something from what the LLM has learned, and apply this as a prefetcher online later on as a heuristic or something? So that's an interesting topic, but remains to be seen. And of course, I would love to see if someone tries to play with this and assume he can build an LLM online. Can you get the perfect prefetcher? Assuming you have infinite storage and infinite compute power, would the LLM give you something interesting? So this is an interesting thing. I'm surprised I haven't seen it yet, maybe in the championship. Oh, no, you have limited storage. But still, like I said, you can just ask the LLM to design a completely new prefetcher from scratch, and then we're all going to be out of work, and we'll have to find a new topic for DPC5. And with this, I will conclude. Was there any questions? Sorry, a little bit of that. We solved all the problems.
Otherwise, so
Thank you.
So our next presenter, please.
Uh, Hello, I'm Hoja Lee from Yonsei University, and today we're going to talk about an architectural blind spot in current multi-level prefetchers and show how we can exploit it to improve performance. So let's start with how multi-level prefetchers work. A prefetcher's characteristic and behavior depends on where the prefetcher is placed. So if a prefetcher is placed at the L1, the prefetcher can see all memory accesses and works on virtual address. But because of the limited capacity and because of the view of the full memory access stream, it works somewhat more conservatively. On the other hand, if the prefetcher is placed at the L2, it sees a sparser memory stream, the midstream from the L1 cache, and works on physical address. And because of the sufficient capacity and the sparser view of the memory access stream, the prefetcher can work more aggressively. And because of these characteristics and behaviors, each prefetcher naturally exhibits a different effect. The L1 prefetcher mainly reduces the L1 MPKI, and while the L2 prefetcher mainly reduces the L2 MPKI. And this can be supported by a very simple experiment here. So we measure the MPKI at each cache level under different prefetcher configurations. Here we compare the L1 only prefetcher with Berti, and an L2 only prefetcher with Pythia, and a multi-level prefetcher that combines both. And the MPKI is normalized to a no prefetcher configuration. And as shown in the figure, we can see that the multi-level design achieves the L1 MPKI reduction identical to the L1 only prefetcher. This is very straightforward because an L2 prefetcher never prefetches to the L1. But an interesting fact here is that the L2 and LLC MPKI is also comparable to the L2 only prefetcher. And this indicates that each prefetcher remains effective at its target cache level, showing this clearly distinct effects. So we can see that the L2 prefetcher reduces the L2 and LLC MPKI more effectively than the L1 prefetcher by capturing long-range access patterns. However, the fact of the matter is that there is an inherent limitation in physical address-based prefetchers. Because L2 prefetchers operate on physical addresses, they cannot safely cross page boundaries. And the hardware doesn't have any information about whether the next page belongs to the same process, or whether it has to require permissions, or whether it is whether it is a part of a large page mapping. So allowing these prefetches could lead to security risks, including potential side channel attacks. And as a result, the hardware just dropped the prefetches beyond the 4 kilobyte boundary, even when the access pattern is very easily predictable. So this inherent limitation fundamentally limits the long-range coverage of deeper level prefetchers. So to illustrate the missed benefits of page cross prefetching, let's just consider a very simple example here. Let's just suppose an application that generates a continuous data access stream that is highly predictable and spans multiple pages. Even though the access pattern itself is very easy to predict, physical address prefetchers just are constrained by page boundaries. They must wait for an access to arrive in the next page before issuing any prefetches within that page. So as a result, prefetching is delayed at every page boundary, breaking the continuity of the access stream and hiding long-range patterns. This effect is reflected in the results shown in the right. To quantify the potential benefit of page cross prefetching, we modify Pythia to operate in the virtual address domain and enable page cross prefetching. Note that this configuration is not architecturally realistic, but we just do it for an Oracle experiment to estimate the performance headroom. And as shown in the figure, we can see that enabling page cross prefetching significantly reduces the MPKI at both L2 and LLC, revealing substantial headroom that is otherwise left untapped by conventional multi-level prefetchers. So furthermore, to gain deeper insight into the impact of page cross prefetching, we compare 3 L2 prefetcher variants on top of the multi-level prefetcher baseline with Berti and Pythia used in DPC4. So we also enable large page allocation here, and we evaluate Pythia operating on physical addresses and on virtual addresses with and without page crossing. And all speedups are normalized to the physical address-based prefetcher without page crossing. And note that these setups are also not realistic. They're just used to get some insights. So what we observe here is that using virtual address without page crossing provides a little benefit and behaves similar to the baseline. But once page cross prefetching is enabled, both physical and virtual address-based prefetchers see clear performance gains. But also, the virtual address-based prefetcher consistently outperforms the physical address one. And this is because virtual addresses preserve access continuity across pages, giving the prefetcher a cleaner and more stable view of the access pattern. In contrast, the physical address-based prefetcher physical addresses fragment streams at page boundaries, resulting in noisier training, less accurate prefetchers, and increased cache pollution. So to exploit the performance headroom of page cross-prefetching, we must address the structural blind spot in current multi-level prefetchers. The L1 prefetchers observe virtual address, but lack sufficient look-ahead, while the L2 prefetchers provide the look-ahead, but operate only on physical addresses. And as a result, huge performance headroom is left untouched. So there are two possible ways to resolve this limitation, either making the L2 prefetcher virtual address aware, or providing the additional look-ahead of the L1 prefetcher. However, enabling virtual address operation at L2 requires additional data paths and TLB access ports and careful handling when the L2 cache is shared by multiple cores. So it's architecturally more complex. So instead, we choose to increase the look-ahead of the L1 prefetcher, which already sees virtual addresses and does not require much architectural changes. However, simply making the L1 prefetcher more aggressive is not sufficient. It must be done carefully under several practical constraints. First and foremost, the L1 cache has a very limited storage budget and must coexist with existing L1 prefetchers. And therefore, we choose a simple IP stripe prefetcher that can capture contiguous streams across pages with minimal state, capturing the multiple page spanning. And at the same time, we need deeper look-ahead to exploit page cross locality, but without significantly increasing bandwidth consumption. To achieve this, we increase the prefetch degree while operating only on the L1 misstream, which is much sparser than the full access stream. And finally, aggressive prefetching must not pollute the L1 cache, so the prefetch lines are filled into the L2 rather than L1, preserving the L1 capacity. So based on these design choices, we propose VIP, the virtual interpage prefetcher. VIP is a lightweight extension on the L1 side that enables timely page cross prefetching on behalf of the L2 prefetcher, while keeping both existing L1 and L2 prefetchers unchanged. So modern processors already store virtual address and instruction pointer information in each MSHR entry to support replay or page fault and coherence handling. So VIP leverages this existing metadata to observe the L1 misstream in the virtual address domain. At its core, VIP employs a simple IP stripe prefetcher trained on the L1 misstream. And like an L2 prefetcher, VIP operates on L1 misses. But unlike L2 prefetcher, it observes these accesses before translation, allowing it to learn interpage stripe patterns before being fragmented. And when VIP predicts the next virtual address using IP stripe correlation, it performs a TLB lookup and then injects the prefetch directly toward to the L2 by passing the L1 to avoid pollution. In this way, VIP supplies the missing page cross predictions, while the conventional L2 prefetchers continues to handle intra-page locality, providing complementary coverage without architectural disruption. Although L1 storage is extremely limited, VIP remains lightweight. In the DPC4 baseline, Berti and Pythia already consumes most of the available space, leaving only about 2.5 kilobyte for additional L1 side prefetchers. VIP addresses this in two ways. First, it uses an IP stripe prefetcher, which is inherently lightweight due to its simple low-state design. And also, it operates on the L1 misstream, which is much sparser than the full access stream. So this sparsity allows VIP to learn stable stripe patterns with very few entries. So as a result, the entire VIP structures requires only about 0.53 kilobytes of storage, well within the remaining L1 budget. The overall VIP introduces performance by 4.77% geomean across 132 workloads provided by DPC, showing consistent gains on top of Berti and Pythia. The AI workloads see the largest benefits because many AI kernels traverse long virtually contiguous memory regions where page boundaries would otherwise introduce frequent L2 or LLC misses. And VIP effectively removes these page cross stalls. Spec and graph workloads show moderate gains, reflecting a mix of regular and irregular access patterns where page cross locality exists, but it is less dominant. In contrast, Google production traces show a small regression. These workloads are control heavy with limited long contiguous data streams and are less sensitive to data side misreduction. In such cases, additional data prefetching can actually slightly increase cache contention without providing enough benefit. So overall, these results show that VIP is most effective for data-intensive workloads with strong virtual contiguity while remaining stable and non-pathological across diverse workloads. Thank you.
Hi. Uh, okay. Just a question. The baseline prefetcher that you use for the L1D is the prefetcher that was given in the for the championship, right? The Berti that was given for the championship. Okay. Yes.
So I have a question. So when you observe that, cross-page prefetching only makes sense when we're prefetching in the virtual address region, do you see in the headroom study itself, do you see any bias towards some workload category that disproportionately improves anything that you find out interesting? This can be like a headroom study, but still like
Yes. In this experiment, we can see that we enable virtual address in the L2 cache for Pythia and page cross enabling in Pythia. What we saw interesting here is that the Google workloads actually show the limited performance headroom in a lot of prefetchers, but enabling Pythia in virtual address and enabling page cross prefetching can actually somewhat capture those performance in Google traces, about like 2 to 3%. I hope I thought I saw. So I think this might be an interesting topic in the future research.
Thank you. That makes sense. Any other question? Okay, if not, then let's congratulate the people once more. Thank you. Who is the next presenter?
Howdy, everyone. So I'm presenting SPAM, the Signature Pattern Prediction and Access Map Prefetcher. This was a work out of Texas A&M University. I was the lead designer behind it, McCoy Merrill, but it was also a collaboration between myself, Lei Wang, another graduate student, and professors Stavros Kalafatis and Paul Gratz. So I'll start with just a brief introduction about the motivation behind SPAM with some background on two relevant prefetchers, the actual design, our evaluation, and finally the conclusion. So as you all know, processor speed continues to outpace system performance. This memory wall behavior doesn't just limit conventional processors, but also GPUs and other processors. And so hardware prefetching has continued to be the major way of fighting this memory wall. Our recent work suggested that even considering bandwidth availability in processors, an ideal prefetcher that's 100% accurate, timely, and has maximum coverage can still receive around 50% speed up over the state of the art. So there's plenty of room here for prefetchers to improve performance. There's been many prefetcher designs that have been proposed. The two I'm going to focus on are AMPM and SPP. Both of these have been implemented in real processors. AMPM won the first data prefetching championship, and SPP is a much newer prefetcher that could be considered maybe more advanced in some of the techniques, but as we'll see, still has significant drawbacks. So AMPM actually relies on hard-coded pattern detection. So it's kind of a dumb prefetcher in that sense, but it's using kind of a robust system where it's looking at the previous spatial history in a region to determine the next prefetch to issue. SPP, on the other hand, is trying to do online learning. So a lot of what the patterns it's learning are complex, and it wants to speculate deeply, but at the same time, it's susceptible to noise and other system out of orderness that you have from the out of order processor, but also how the caches manage requests. And so SPAM, our prefetcher, is trying to solve both of these problems at the same time. Also note here on the graph, under our evaluation, AMPM actually outperforms SPP and IPCP, which were, well, IPCP won one of the previous championships. So just some background on AMPM. So it splits the address space into regions. You have bitmaps for each of these regions that track what blocks in that region, let's say a page, have been used. When the access map is populated enough, AMPM will recognize a pattern, and then it will pull in additional blocks. And on top of this, AMPM is tracking what it's pulled into the cache, so it won't prefetch something that it expects to already be in the cache. So you save some bandwidth there. And here's an example. So a access might come in at region AA, offset 3. So AMPM is going to set the bitmap for that position. It'll do this for any address coming in, but eventually a pattern may emerge. So for example, we have 3 blocks that have been used consecutively in this region. AMPM is going to recognize that pattern, and it's going to grab the next block. SPP, on the other hand, is kind of similar in the sense that it's tracking regions, but instead of using these access maps, it's just doing a delta signature. So these are the last 3 jumps into the region. So you come up with the signature and you try to predict the next delta. And SPP is adaptively learning as it goes. So over time, it may choose to use one delta over another. And essentially, it's trying to do a partial pattern matching or trying to generate Markov chains for its predictions. It's also using an access filter to try to filter out recently prefetched blocks, so it's not occupying all the queues with bad prefetches. So here's an example. An access comes in at region BB, and we will consider the new offset with the last offset, which we'll see as a delta of +1. We'll update our signature with this new value, and we'll also send the old signature along with it to the pattern table. SPP uses this old signature and the new delta to increment the confidence it has for a particular prediction. And then it's going to use the new signature to make its own prediction. And then SPP is going to pursue essentially an A-star path down this Markov chain. So it's going to now use that prefetch of +1 to create a new signature and keep indexing to find what the next delta should be. So it can prefetch to some arbitrary depth. So AMPM is limited in the sense that it's not really learning anything. So it has to conform to the most common outcome of a pattern. SPP, on the other hand, can learn, but it's really sensitive. So this delta method is really sensitive to reordering. A +1 stride you would think is just being a +1, +1, +1 delta. But SPP could represent that in numerous different ways. You could end up with 2, -2, 1, or 1, 2, -1, all representing the same thing, but blowing up the amount of state you have in your pattern table to try to store what is essentially just a +1 stream. On top of this problem with occupying a lot of entries in your pattern table with SPP, each signature, when you're doing this Markov chain traversal, each signature can only map to as many other entries as you have deltas. So a single node in your graph here is only going to go to, at most, 6 or 7 other graphs nodes. So the motivation behind SPAM is that this longer history the AMPM has is useful, not just because we retain a longer history so we have more context, but we can afford to wait before committing that history. SPP, on the other hand, has to learn on the fly. It's not storing a lot of previous information, so it can't choose whether not to commit something to memory. Techniques like SMS are utilizing this reordering kind of resistant learning, where we're waiting for a page to go out of scope before we learn from it. But the same issue is that SMS is kind of not generalized. It's using a IP or a page offset as an index, which can mean you miss potential triggers that would have been useful. So SPAM is trying to go beyond all these previous limitations and come up with something that's very general so that we aren't missing any potential triggers that are going to be useful for pulling in entire regions. So here's an example of how SPAM's region table is managed. It's just the same as AMPM. We are marking blocks that have been accessed within each region. However, this time we return the spatial history behind the current access for that region. So now we're going to send, in this case, 101 to the pattern table. We're going to look up that entry in the pattern table for that particular spatial pattern, and we're going to come up with the next 3 blocks and which ones of them are going to be used. In this case, we just choose to grab the next one that's marked, which is at a +2 delta in the future. We can then use this prediction of what we think the next 3 blocks and which ones are going to be used to reindex our pattern table just like SPP, so we can prefetch to an arbitrary depth. So SPAM is actually utilizing the access map as its history. So it can wait until all the references in a pattern are complete until committing it to memory. So instead of committing what might be a reordered pattern or some pattern that kind of aliases to another one, we're waiting for all the accesses to arrive, get utilized before we learn. The heuristics SPAM is using to wait before it's learning are the time since the last access. So essentially whether the region has gone out of scope, may not have been evicted from our region table, or whether we've accumulated a lot of accesses. So this region is particularly busy, and so we want to try to learn from it since it's generating a lot of accesses. So with either of these go to 0, SPAM will trigger its learning phase, and it will essentially go through here with a rolling window and generate a bunch of different prediction pattern pairs. All these will be sent to the pattern table, and we'll go through one by one and increment the confidence as those different patterns occurred. So over time, SPAM is actually going to compile a pretty complex pattern status, which is going to be encoded in the pattern table. This is an example of using a 6-bit pattern when you're using SPAM. This one is actually generated from Spec 2017's NCF workload. And so what's encoded here is essentially a graph. And SPAM is now going to use essentially A* to navigate the most confident edges in that graph to generate what it believes the region will be. So for example, we might begin traversing at 0, 1, 0, 0, 1, 1. We'll find the most confident entry in that row and rinse and repeat. We're going to generate a lot of different accesses that are essentially reconstructing what we believe the access map is going to look like in this region when it's done. And so with 4 table references, we were able to generate 18 prefetch targets. And well, note here is that since this is from a real workload, you'll see that the patterns generating is actually symmetrical. So of what it just generated, despite using various different entries in the table, it's coming up with a coherent pattern. Besides generating all these prefetches, spam has to determine some way to drop the ones that it believes aren't going to be useful, either because they aren't going to be timely or they're going to saturate the bandwidth. And so every time a useful or useless prefetch is determined by spam, it's going to re-reference the region table and try to figure out which pattern generated that prefetch. And then it will try to track the usefulness of different patterns. And that means that a particular node in spam's graph is going to essentially become a dead node. So anything that ends up going there gets squashed and we stop traversing. If the region table's entries aren't lasting long enough, so we see a useless prefetch come back, but the region's no longer in the region table, then we just fall back to using the global usefulness. So besides just kind of tracking it that way, the usefulness is also going to determine how many prefetches can be issued along a certain path and whether or not spam is going to probabilistically start dropping prefetches as they go down that path. Here's a large scale overview of how we integrated spam into our system. So we have Berti in the L1D that's been slightly modified to include a larger filter. We have Bingo in the LLC. Which is acting as our last level cache prefetcher, and we have spam situated in the middle in the level 2 cache. Spam is receiving information from both of these prefetchers. So from Berti, it's receiving page associations. So it tries to jumpstart its prefetching process in a new region by knowing what the previous region was, thanks to Berti's page traversals, since it's in the virtual space. Bingo is reporting the LLC occupancy to spam. So spam is actually doing multi-level prefetching. So if it believes a block is already in the last level cache, it will not prefetch it to the last level cache. And finally, we found that Berti is actually training spam quite well. So spam is training both off demand and prefetch from the L1 cache. And finally, Bingo is just acting as our fall-through prefetcher. So if Berti isn't picking up on a pattern and spam isn't picking up on a pattern, then Bingo is sitting there in the last level cache to try to learn from these prefetchers that are falling through. Our final speed up on the first set of traces that were released for DPC4 was around 6% for both regular single core and limited bandwidth. We found our best workloads were MCF as well as Zlink BMK from Spec 2017. We also saw general performance speed up across all but a few workloads. Of note here are 4 different workloads where AMPM, traditional AMPM, outperformed spam, suggesting that spam might be having trouble learning on these workloads. And it might be too slow or to adapt, or it might have trouble with it within its pattern tables with aliasing or other corruption. Our evaluation in multi-core was not as great. We saw a 2% slowdown on our of 50 mixes. We didn't spend any time trying to optimize or tune for multi-core. So this was kind of expected in the sense that spam is being far too aggressive for multi-core, which suggests that our heuristics for throttling ourselves are not correct. In conclusion, spam is still a fairly unoptimized design. There are clearly better heuristics we can be using to trigger learning besides just timers. SMS had work done with timely learning through tempo, so that might be helpful. There are other questions of the ideal pattern length. So we found that 6-bit patterns seem to work best for spam. But we know that things like branch predictors get by with single-bit predictions. They don't need to predict that far in the future. So it might be that we might want a more narrow prediction than we have for a pattern. And additionally, spam is throttling itself probabilistically, which isn't great because we could probably assume that some of those prefetches, even though they're coming from a more useless node, those prefetches that are closer to the original target are probably more likely to be useful. More importantly, the general trajectory we found with spam, if you plot from SMS to AMPM to SPP, is that we're essentially going down the same route branch prediction has gone down, with partial pattern matching becoming the ideal of how do you learn a pattern. And that gives us all kinds of questions like, can we use branch predictors to actually prefetch? Since we just need to predict a single bit here for SPAM to be able to recursively access these tables, a branch predictor could drive SPAM's predictions. The other thing is DRAM aware things. So SPAM can prefetch great distances throughout the access memory space, which means for larger pages, even 2 megabyte pages, you might be able to exploit features of DRAM bandwidth to get more bandwidth out of the DRAM than a typical prefetcher would be capable of. And that's all I have. Thank you.
Thanks, McCoy. Any question from McCoy?
Very nice work. Thank you.
Thank
I liked the presentation and I think it was very clear, the idea. I have a question with the first graph that you show with the comparison. Can you go back there, please?
Yep. This is the problem with having a lot of animation.
Yeah. But it makes very clear all the concepts. So that's good.
Here.
Okay, here. Yeah.
Yes.
So first question is, this is L1 or L2?
So this has, for example, IPCP has a L1 and an L2 engine in its prefetcher. So in this particular thing, IPCP is in the L1 and the L2. Bingo is in the L2. PPF is in the L2. Berti's in the L1. AMPM in this graph is actually in the L2. A lot of implementations put it in the L1, and they might use a virtual space. Here we just have it as the L2. Berti and PPF, right? So we have Berti in the L1, PPF in the L2. And for Berti and AMPM, it's the same thing. Berti's in the L1, AMPM's in the L2.
Okay, so what is Pythia here? It's like, were you able to run it? It's, more or less.
So this is these are graphs from a different trace suite that we had before DPC4. So these are actually numbers from that, which is why we aren't running Pythia in these sets.
Okay.
But it is interesting that AMPM, Berti plus AMPM, does perform better than Pythia in our DPC4 experiments. So it suggests that Berti and Pythia is probably somewhere between Berti and PPF and Berti and AMPM.
That's why my follow-up question, because we did the same, we did a similar experiment with AMPM in L2, and we saw that for some traces was better than Pythia, for others no. The mean was, so my question is, you use exactly the AMPM that is in the stable version of Jamsim, or did you do any?
No, so we have some modifications to the version we were running. A couple of things with the version that's shipped with Jamsim. It's meant to be used in the virtual address space. What we find is that it's not really great for the virtual address space, and it's meant to be used in the L1. Our L2 version of AMPM is similar. It's very conservative. The main difference here is that AMPM is also checking evictions in the cache to determine its access maps. And so it's allowed to re-prefetch things if they get evicted from the cache. And that's the main difference between the shipping version of AMPM and the one I'm showing here.
Okay, thank you. Thanks a lot.
Sorry, quick one. Actually, two questions if there's time. So you said 6 bits to encode the data. Does that mean that these are 6 bits of a bitmap of which cache lines? So you're actually 6 bits wide, or this is an enumeration of all the larger patterns?
Yeah, so SPAM is keeping a full 64-bit map for every region.
Okay.
So whenever there's an access, we're just grabbing the previous, including the current access, the previous 6 bits. We're then feeding that to the pattern table, and we're making a 6-bit prediction on the output.
Okay.
So I have a slide at the very end, which we may not be able to get to.
No, it's fine. Yeah, okay.
But,
the answer.
What this ends up making is a really nice graph of essentially nodes that are marked by a 6-bit identifier, and it kind of graphs how those are all connected.
Okay, so you can access this using this as an index, the 6-bit index.
Yeah.
Okay.
So I'll give you a better idea, which is in this. So this is that same pattern table encoding that I showed in the main presentation, except it's graphed out. And so this is for MCF. You'll notice this is the one I traverse in the example. There's also this one. The only difference between these two, by the way, is how you enter them. So one will terminate with a repeating sequence. The other terminates with all ones in a repeating sequence. And so SPAM is essentially able to differentiate between these two specific modes that are happening in MCF and predict those. But it's essentially just a graph traversal. So a node name in, node name out, essentially.
Okay, thanks. This also answers my other question, which was, do you suffer an explosion of or overfitting of the problem? But if you're using more specialized training, so this means you don't have that problem. Yeah.
Yeah. So if you were to see, yeah. So if you were to like try to do offline training or train on across all the workloads, you end up with essentially this problem where you overfit to everything either is a 0 prediction or everything's either a 1 prediction. And that's an example I have here in this slide.
Great, thanks.
I have just a quick follow-up. We're also running out of time. So the choice of having 6 before 6 after that sounds arbitrary, right? So do you see any
width
sense?
is arbitrary, of course, and the width of the prediction, they're both arbitrary. You could size them.
Exactly.
However,
so do you see any utility of sizing it differently for different workloads? And then that, if workload is like AIML workloads, we also saw that it's mostly spatial, right? Like you can go as aggressive as possible. So there may be, having a bigger length per spatial bitmap prediction output, like the output length would be bigger. Does that help or?
Yeah. So what we found generally was that having a wider output isn't too helpful when you have look ahead. So for example, if we only predicted 1 bit, we could just do look ahead like SPP does, and we could
Piggyback each other.
keep going to an arbitrary depth with just a single bit prediction.
Mhm.
What's more important is the pattern that encodes that single bit. And this is something you'll see in like branch prediction with the same principle. The interesting thing we found was that shorter patterns, they learn faster. And for workloads that are very +1 oriented, Photonic in Spec 2017 is a great example of this. It's much better just to do that. In fact, you see more performance that way. For other workloads that have more complex patterns like MCF, using a larger pattern like 7 or 8 bits gets you more performance, but then you become too conservative on your other workloads. You take too long to learn and you lose performance. So we found 6 was a really nice middle ground of where we weren't too aggressive and we weren't too conservative.
Thanks. Any other question? I think we can take only one. Okay. Let's have one more.
Thank you. So I am actually from the branch prediction communities, and I find it quite interesting. You mentioned PPM in your design, and I'm giving a question just a follow up of the just now questions. Did you try using more complex algorithm? In branch prediction we have TAGE, and it uses geometric length of your pattern. So did you try using adaptive algorithm to select the signature length, or using XOR hashing word?
So we did initially try using multiple different history length tables, kind of how you might see from a branch predictor. What we found was that, at least in the amount of time we had, there wasn't enough time to set up the necessary context. So a spatial context doesn't seem sufficient to use longer patterns. For example, if you had 16-bit patterns, we run into this really bad aliasing problem where it just kind of it gets drowned out by noise. However, we are trying right now just to use single bit predictions to see if we can just substitute in a branch predictor using this method and see what kind of performance we get. So that's the current area we're trying to go down with this.
Okay, thank you.
So let's thank the speaker once more. Okay, our next speaker is Jiaji, I believe, from Shinova. He's going to talk about Emender, optimizing prefetch priority and throttling in vBerti plus Pythia.
Hello, everyone. My name is Qingji, and I'm presenting on behalf of my team from Tsinghua, led by Jiajie. We have Xiaoyi, Xuefeng. Our work is called Emender, which focuses on optimizing priority and throttling based on sBerti and PASIA. Here is the agenda of my talk. I will explain the specific problems we found in existing solutions, and then we will detail the 4 key optimizations we designed to solve these problems, and finally, we show our evaluation results. Let's briefly look at the background. As we all know, we face a memory wall problem. Processors are getting faster, but memory speed isn't catching up. That's why data prefetching is crucial today. And the goal is simple. We need to predict what data the CPU needs and load it into the cache before it's actually requested. Our work builds on this foundation, focusing on how to optimize SOTA prefetchers like sBerti and PASIA to better utilize limited prefetch resources and improve multi-core fairness. Okay. Our first step was to find the current SOTA prefetchers. We evaluated 13 different prefetchers, ranging from early classics like SMS from ISCA 2006 to recent ones like GATE from HPCA 2025. We ported all these prefetchers to the DPC4 simulator. After testing many combinations, we found that combining sBerti at L1 and PASIA at L2 gave us the best baseline performance. You must say Berti and sBerti mentioned. Berti from DPC3 use physical address for prefetching, and sBerti published at macro 55 is an enhanced version that uses virtual addresses. And sBerti's virtual addressing approach generally performs better in our evaluation. So we choose it as our baseline. During testing, we face a big practical problem, evaluation time. Running a full simulation for one configuration took about 1 day. With so many parameters to tune, we couldn't test everything. So in fact, we tested traces at just 1% of their length in most cases. And we found that the relative ranking of the prefetchers at 1% was consistent with the full 100% run. So this allowed us to test 100 times more combinations and finally choose the sBerti and PASIA. With our baseline selected, we conducted detailed profiling to understand what was limiting performance. The combination of sBerti and PASIA is very aggressive, and it generates a massive volume of prefetch requests. The problem is that the prefetch queue is limited, only 8 entries in the standard configuration. Our tests show that the prefetch queue is full in 80% of the time, and most of prefetch requests were being dropped due to a full prefetch queue. So this gave us our key insights that we must use the limited prefetch queue more efficiently. We identified 2 approaches, prioritization and filtering. For prioritization, if the queue is full, which requests should go first? We need to make sure the most useful ones to get priority. And the original sBerti only prioritized within the same load instruction. So we saw an opportunity to prioritize globally across all load instructions. For filtering, we noticed many prefetches were fetching data that was already in the cache, which is a waste. The challenge is that we need a cache membership query with minimal hardware overhead. Our first optimization is a pending target buffer, PTB. It's a global waiting room, and before sending requests to the queue, we put them here first. Each entry contains the cache line address, confidence level, status, IP hash, sequence ID, and a failure count. We implement several policies, duplicate filtering within the buffer, replacing the lowest confidence entry when the buffer is full, and eviction of entries with excessive failures. The buffer uses very little hardware, about 860 bytes. This simple but effective mechanism ensures the best prefetchers get sent first, and making optimal use of the limited queue capacity. Our second optimization is the cuckoo filter. The goal here is to stop prefetching data that is already in the L1 cache. So why not just check the cache tags? We think checking the tags requires read ports, and we don't want to interface with the CPU's actual work. So we use a cuckoo filter, which is similar to a bloom filter, but it has better storage efficiency and have deletions. It tells us if an address is in the cache with no 0 false negatives. The hardware cost is about 6.5 kilobytes, where each entry contains a valid bit and a 12-bit fingerprint. If the filter says it's not in the cache, we can simply prefetch. And when it says the data is in the cache, there is a small chance that it's wrong, meaning we might occasionally miss a useful prefetch. But this false positive rate is low enough that the trade-off is worthwhile. Okay, implementing the cuckoo filter had a tricky technical challenge. The L1 uses virtual address for indexing, but physical text. Sometimes different virtual addresses point to the same physical data. This aliasing could confuse our filter. So to fix this, we add a small mechanism to track the last accessed virtual address for each cache line, which needs 22 bits for an index and fingerprint, and is used for cuckoo filter updates. The reason this works is in the most case, the same virtual address is used repeatedly, and aliasing is relatively rare in practice. So generally, this is acceptable. Okay, our third optimization deals with unpredictable patterns. We observed that some load pieces have semi-unpredictable patterns. For example, accesses might follow a pattern like A plus 2, B plus 2, C plus, and so on, where A, B, C are relatively random accesses. The problem is that the data 2 appears frequently, and the prefetcher learns this pattern and uses it, prefetching A plus 4, B plus 4, C plus 4, which are often useless. Our solution is per PC throttling, which tracks the miss rate of each instruction. If an instruction causes too many misses, we ultimately raise the bar and throttle it. If it starts doing well, we let it prefetch more. So it adapts effectively to the pattern. The hardware cost is minimal, just 10-bit miscounter per Berti table entry. This provides self-adaptive throttling that further reduces useless prefetches. And our final optimization focus on multi-core performance. Berti and HPCA is very aggressive. In a multi-core system, one core can hook all the memory bandwidth, serving the other cores. This hurts the overall score because the computation metric uses harmonic speed up and penalize unfairness. So we introduced cross-core coordination. First, our L2 prefetchers report useless prefetch statistics to L3. L3 aggregates these statistics from all cores and identifies the worst offender. that's the call with the highest useless prefetch count, then it throttles that calls prefetching. So this restores fairness and yielding better overall performance. The hardware cost is only 64 bytes, not kilobytes, 64 bytes for counters. Okay. Here is a full picture of our solution. At I1, we use sBerti enhanced with our pending target buffer, Cuckoo filter, and dynamic threshold. The total storage is 23 kilobytes. And at L2, we use PCA with extended throttling logic. It needs 26 kilobytes. And at L3, we don't prefetch data here. Instead, the L3 only serves as a fairness coordinator and requires only some counts. So the key design principle is hierarchical optimization with coordinate metadata exchange across all cache levels. Okay. For our evaluation, we use the standard DPC4 championing framework and tested 3 standard configurations provided: single core with full bandwidth, single core with limited bandwidth, and the 4-core system. We also report our score using the standard scoring methodology, and our baseline was Berti at L1 plus PCA at L2, and no prefetcher at L3. Okay, let's look at the results. The graph shows our speed up compared to the baseline and other prefetcher combinations. Emender is the brown bar on the far right, and for single core full bandwidth, we see a 6.6% speed up. That's an unconstrained memory bandwidth scenario, where our optimizations improve the prefetch accuracy. For single core limited bandwidth, we achieve a 2% speed up. This is the memory constraint scenario and showing a smaller but still significant improvement. For multi-core system, we achieve a 6.1% speed up. And here the L3 throttling improves fairness and harmonic speed up. The final score improvement is 4.8%. We also did an evaluation study to see which feature helps the most. The Cuckoo filter top row gives the biggest boost in single core performance because it saves bandwidth and it has have a contribution of 0.8% overall. The L3 fairness throttling was helpful for the 4-core test, improving it by 2.6% and 0.9% overall. The dynamic confidence threshold and the pending target buffer improve overall performance by 0.1 and 0.2%, and they serve as a foundation of other optimizations. Okay. Finally, we want to make sure our design was robust. This S-curve shows the speed up distribution. As we can see, the vast majority of our workloads are above the dashed line, with a median case shows about 1.1 times speed up, meaning the majority of workloads benefit. And there are very few regressions, and against in the best case are significant, over 1.4 times. Okay. To sum up, Emender is built on top of the powerful Berti and PCA prefetchers, adding 4 key optimizations. First is pending target buffer for global priority. Second is the Cuckoo filter to stop redundant prefetching. And third, the dynamic thresholds to adapt to difficult patterns. And finally, the L3 fairness throttling to coordinate multi-core systems. Okay, this work demonstrates a systematic optimization approach and shows the value of cross-level coordination. Finally, I'd like to discuss some implementation considerations and future work. For hardware reality, our Berti table is fully associative now, but a real chip may would like use 16 set and 4-way design. For the PTB, the full hardware sorting for the PTB is costly, so we can use a few priority buckets instead. And the prefetch filtering we already felt with Google filter plus setup, and maybe we should compare it with a shadow catch, recent access filter, or perception options. Okay, thank you for listening. Any questions?
Any question for Chachi?
So I saw you built your optimizations on Berti and Pythia, but I don't think any of the things you did are really super specific to Berti and Pythia. Have you tried generalizing them to a bunch of other prefetchers yet?
Yeah, it's not specific to Pythia or WebAssembly, but because other prefetchers performs a big gap between Berti and Python, so maybe we can try it later.
Okay.
For the interest of time, we should go ahead with the presentation. So let's thank the speaker again. Okay, so our next speaker is Jiaping Shou. I guess I'm pronouncing your name correctly. So he's going to present sBerti, enhancing Berti with a smart stripe prefetcher for better coverage. I think lots of DPCs are coming from Berti variants.
Okay. Hello, everyone. I'm Xiaopeng Zhou, and I'm a first-year PhD student in HKUST Guangzhou. Yeah. It has been 7 years since the last DPC event. And in DPC4, 3 kinds of new traces are introduced. That is graph, the Google Traces version 2, and AI ML workloads. There is also a large storage budget and a new configuration of limited bandwidth. This brings new challenges and new opportunities. Firstly, prefetchers should strike a balance between different patterns of applications from different categories. And typically, a prefetcher modification can increase the IBC of some workloads while degrading the others. But as more traces are introduced, we should consider the impact on applications in more categories when making the changes to the prefetcher, which adds some complexity. And additionally, the newly introduced limited bandwidth configuration require us to throttle the prefetchers based on the real-time bandwidth and make the prefetchers accurate. But there is also an opportunity to profile and analyze memory access patterns for the new traces. Prefetchers which perform the best in previous contests may also fall short on new traces. So our strategy is to find patterns not covered by the baseline prefetchers and incorporate a lightweight prefetcher targeting the missing patterns. We hope the profiling and analysis will provide some insights to the community. I think our solution is similar to the first presentation. And we also find some cross-page issues in the default DPC3 Berti prefetcher. But differently, we just add a simple stride, decoupled stride prefetcher in the L1 data cache to cover this cross-page misses. So firstly, we analyze the L1 decache load miss rate of the baseline. This figure shows the results clustered by categories. We notice that there is high L1 decache miss rates for AI ML workloads and the graph workloads. And the spec 17, I think it is well studied in previous championships. And the Google Traces version 2 has a high instruction miss rate and low data miss rates. So we will many focus on the AI ML and the graph workloads. So next, we analyze the traces of the graph and the AI ML workloads. We found that graph workloads show an indirect memory access patterns, which is like an ABI array access. And I think that is well explored by previous researchers. However, in DPC4 traces, there's only load address and no load values of the memory accesses. So we cannot get the value of the BI, so which makes it difficult to predict address of array A. So I think the prefetcher in this context is also not allowed to get a value in the cache. So we will mainly focus on the AI/ML workloads, especially for llama2.c. We found that there is a dominant stream access patterns which causes a high L1 data miss rate. So yeah, this page. Then we will dive more into the prefetch. I think the observation is also similar to the first presentation. We analyze the memory access, the prefetch and memory access of the DPC3 Berti on llama2.c workloads. The figure in the right displays a memory access snippet of llama2.c. The x-axis is the cycle in the transient, and the y-axis is the memory access address. The blue dots represent prefetches, and the orange ones represent L1D hit and useful prefetches. Since there is no data reuse in the stream access patterns, so all the L1D hits are useful prefetches. The red dots represent the L1D misses. So from the figure, we can notice that although the Berti, the DPC3 Berti can cover most of the stream accesses, a large amount of misses appear every 4 KB across the page. I think this is similar to the first presentation, which means the Berti cannot cover this layout. So we are looking for suitable prefetchers such as stride 1 to cover this simple stream pattern. And we have also tried some combinations to combine the Berti with other prefetchers, such as temporal ones. We only get better overall results when incorporating a stride prefetcher. So that is attributed to the stream access patterns in AI ML workloads. The stride prefetcher we used in our solution, we call it a smart stride prefetcher. We derived it from the access stride prefetcher in Shangshan, which is an open source high performance RISC-V core. The smart stride prefetcher utilizes a confidence, that is a typical one, utilizes a confidence counter just by comparing the prefetch address against the demand access address. And prefetches are issued only when the confidence exceeds a specific threshold. And to ensure the timeliness, the system monitors the late prefetches and dynamic adjust the prefetch depths. Furthermore, strides are detected at multiple of the data value to adapt to the out of order access patterns. So as some of the, okay, so not this one. So here I compare the sBerti and the original one, Berti in the DPC3. So sBerti is we simply combines Berti and the smart stride prefetcher we mentioned in the previous slide. And these two components issue prefetches independent, and the metadata tables are separate too. And the figure compares the memory access snippets of the DPC3 and the sBerti. From the figure, we can observe that the red dots, which represent the misses, cross-page misses, and in the left, we turn it into orange ones, which means the useful prefetches. That's the comparison figure. And the number of useful prefetches has increased from 846 to 995. So sBerti behaves just like incremental work, like a patch on the DPC3 Berti, but not accurate enough as some of the reviewers have pointed out. So some of the reviewers also ask, can the reproduction in the published in the micro prefetchers, can the reproduction handle the cross-page patterns well? I think theoretically is yes, but in our experiment, we have some problems. The reproduction doesn't work well in our setup. It's unclear whether this is implementation error or theoretical flaw. But now from the third presentation, just the previous one, I'm sure it is implementation error. Yeah, we also discovered some prefetch queue fullness. The prefetch queue is full most of the time, and which results that the prefetch depth is always 1, and the prefetch is not timely. Oh, okay. By profiling, we observed that the stride 1 always have the highest confidence. I think that is related to the full prefetch queue, and the prefetchers with larger strides has less possibility to be issued. And the prefetch request in the prefetch queue, we observe that is always stored, which means there are late prefetchers. And we are still debugging, but I think it is related to the prefetch queue. If we throttle these prefetchers, I think it will achieve a similar performance to the sBerti. Okay, and next I will introduce the overhead. We only have a smart stride prefetcher that only contains the stride detection table and the duplication buffer. And because of the introduced overhead, we reduced the number of record pages in the Berti to satisfy the L1 decache prefetcher budget, that is 32 kilobytes. And next, we will show the experimental results. First is about the coverage categorized by different workloads. The sBerti increased the coverage of AI/ML, that's typically stream accesses, and expects 17 workloads. The coverage of Graph and Google Trace version 2 remains nearly identical, and it is as expected since for the Graph workloads, it is many indirect memory accesses. And for the accuracy, yeah, as some reviewers pointed out, there is a accuracy drop for the categories. I think it is related to the prefetch duplication, and remains for future work to profile of this problem. And we also selected multiple applications which has over 50% stream access patterns and presents the speed up of our sBerti versus the default Berti in the figure below. And we can observe significant speed up in the AI/ML and spec 17 categories. So for our solution, we use sBerti as a L1 prefetcher and the default path as L2 for our solution in the context. We didn't use a LC prefetcher as we failed to find a good solution to get performance gains in both the full bandwidth and limited bandwidth configurations. So in all, our solution achieves slight performance gains around 7% in AI/ML workloads and 2% on spec 17 workloads under the full bandwidth configuration. And sBerti remains nearly identical performance on average under the limited bandwidth configuration. So to conclude, we introduced sBerti, that is a hybrid prefetcher. And it combines the strengths of Berti and the smart stride prefetcher. So the main goal is to address the cross-page limitation of the DPC3 Berti. And in the experiments, sBerti achieves around 7% speed up in AI/ML workloads, but there is still room for improvement. We plan to address the accuracy challenges in the future studies. And we are also looking into the Berti as another promising direction to solve the cross-page boundary problems. So finally, we would like to extend our special thanks to the reviewers for their constructive comments, and which greatly improved our work. And we will also thank the DPC4 organizers for hosting these excellent competitions. Okay, thank you very much. And
So do we have any question or maybe any burning question? We can take it. Anything? Okay. If not, then let's thank the speaker again. And oh, sorry.
I just closed
So-
the presentation.
Can you hear me?
Maybe I can.
So basically, you are replacing the detection of cross-page patterns of Berti with a stride prefetcher. Did you try any alternative prefetcher for these cross-page patterns? How did you end up with an IP stride one? Get my?
So
Can you hear me?
I only heard that the cross.
So how did you end up using an IP stride prefetcher as a complement to Berti for cross-page patterns?
Yeah. The
Did you
prefetcher.
try any other implementation of another prefetcher that could be used as an alternative to IP stride for the cross-page patterns?
So the prefetcher here I use is yes, that is IP stride, and that is complements the default DPC3 Berti, and so
So
and
why did you select IP stride? Is there any reason behind this?
yeah, for the limited time we only tried the IP stride prefetcher, but I think a multi-stream or other stream-related prefetcher will also work. And if we fix the bug in the Berti, I think Berti will cover that pattern either.
Yeah. Cool,
Thank you
thanks.
very much.
So let's thank the speaker again. So that brings us to the close of the first session. We would have a break now till 3:50. So that's 15 minutes break. And then we would come back again at 3:50 to have the second session. Thank you very much.
I just got your email.
Hey Rahul, are you able to see or hear me?
Akanksha, I think I can hear you. So give me, you can hear me, right?
Yes, now I can.
Yeah. So we just had the break. I think we are on time. So we would have, maybe 5 minutes later than what your schedule is. Uh, yeah.
Okay,
So
yes, sounds good. I'm on now. Just let me know when to start. I just wanted to make sure I can.
that's perfect. I'll fix the audio thing and we'll be good to go.
Okay, sounds great.
Perfect. Thanks, Akanksha. I'll
Sure.
see you
Yeah.
soon.
Yeah.
Hey, Akanksha, can you hear us?
Yes, I can.
Okay, so maybe we
I can
just
share.
just give me 1 sec. So I need to give you the permission. Stones. Okay, so you have the permission to share. Can you try sharing the screen?
Do you see it?
Yes. Just give me 1 sec. Then we need to remove the spotlight or multi-speaker. Oh, multi-speaker is fine. Yeah. Okay, so wait, just give me 1 sec. So we're actually people are actually coming back from the break, so maybe we will start in a couple of minutes. Just give me 1 sec. So then it would be good to give Akanksha the view of the room. Sure. Yeah,
Okay, yeah, that's better.
that's better.
Yeah. Yeah, let me know whenever you want me to start. And no rush.
Akanksha, are you getting a good view of the room? I think so.
Yes, thank you.
People are still not back from the break yet, but I think we can start since we have running a bit late. So let me introduce you first and okay, great. Okay, so welcome back from the break. So in this session, we are going to again have 4 talks from the participants and 1 keynote talk. So we will start the session 2 with the keynote talk from Dr. Akanksha Jain. Akanksha is a staff software engineer at Google, where she works on cross-stack solutions to improve data center efficiency. Her work has led to substantial efficiency improvements in Google's existing fleet and has informed the design of future resources. Her research interests are in computer architecture with a particular focus on the memory system and on using machine learning to improve system design. She received her PhD in computer science from the University of Texas at Austin in 2016. So let's just welcome Akanksha. And I need to give a nod to Akanksha because of her team. We got the Google traces that are getting used for this DPC4 championship. So let's all give her a warm welcome. Thanks, Akanksha.
Thank you, Rahul. Thanks for the introduction, and I'm really glad to be giving this talk. I'm sorry I wasn't able to make it in person, but really thankful to the organizers for accommodating a remote talk. So in this talk, I'll sort of give a perspective of prefetching from a data center side. And so just a little bit of background about myself. I've spent majority of my career in academia as a grad student, as a research scientist at UT, and published a bunch of papers on data prefetching. I've attended many of these competitions, which I loved doing. But that sort of gave me a view on academic research in the area. Then I spent a brief amount of time at ARM, where I got to sort of see firsthand how prefetchers, cutting edge prefetchers, are designed in industry and how academic ideas sort of make their way into product. And for the last 4 years or so, I've been at Google, where I've gotten an opportunity to sort of really see how prefetchers that are baked into our commercial microprocessors, how do they work at the scale of something like Google's data center fleet? So we typically have millions of machines and running a lot of workloads, and I've been working on sort of prefetching solutions for those. And so I've gotten an opportunity to really understand what happens there. So in this talk, I'll share some lessons that I've learned from experimenting with prefetchers in Google's fleet. And this is not hardware design in particular. This is sort of playing around with prefetchers in existing CPUs. I'll sort of give some thoughts on my thoughts on what are the implications of these lessons for hardware prefetcher design, and my perspective on if I had a wish list for future competitions, what would that look like? So just to start with, memory bottleneck is a huge problem in data centers, and this should not surprise anyone. I think Google's published plenty about this. 40% of cycles are spent waiting for memory, and prefetching remains a very, very impactful avenue to reduce this bottleneck. However, existing design paradigms, I think, leave a lot of opportunity on the table that we are not taking advantage of. So what do I mean by existing design paradigms? So let's step back and really sort of think about how we design prefetchers today, or really any microarchitectural predictor, right? So we have a set of workloads. We have standard benchmark suites like spec CPU, gap, there's a well-defined set of workloads, which we select as some proxy for this is what represents the universal behavior of all applications. We then run these workloads through a simulator, something like JAMSIM, to sort of see how any changes I make to my prefetcher, how does that impact performance? And then we sort of fine-tune our solutions. You might modulate prefetch degree, distance, your confidence logic to sort of see how you can maximize performance for the common case. And then finally, when you're happy with your solution, you decide this is what I'm going to do. And let's say if you're someone working at in a microprocessor company, you decide a design with certain fixed parameters and you bake that into the hardware, which you then ship. So there are a lot of limitations in this design paradigm when you're thinking about designing prefetchers for scale. So first of all, there's the workload gap. So for the longest time in academia, we've looked at open source workloads, spec, gap, AI, ML that were introduced in this competition. And then typically we evaluate them on 1 core and 4 core systems. And both these things are not a good measure of what would work well at the data center level. So the first lesson that I learned, and this should not surprise anyone, is that spec and gap do not represent data center workloads. They have different program behavior. I think Google published a paper about this a few years ago called Classifying Memory Access Patterns. Data center workloads are multi-threaded versus single-threaded workloads that we typically look at. Not only are they multi-threaded, but they have sort of complex schedules across a large number of cores, and there is a high degree of multi-tenancy. And so one thing that we tried to do with this competition was to provide the community with some traces that represent Google workloads. And a big thank you to the organizer and a special shout out to both Rahul and Matthew Giordano from University of Washington to sort of take the traces that we had in a different format and convert them to a JAMSIM format so that this could be used for the competition. This was a last minute request, so I'm very grateful to the organizers for accommodating it. What you will see in these traces is that we have about 13,000 threads, traces from 13,000 threads across 12 workloads. And each individual workloads has 4 threads to maybe 1,000 threads workload. It varies across workloads. These 12 applications capture salient characteristics of data center workloads. You will see large data footprints, large instruction footprints, complex schedules, multi-threading. So I broadly encourage folks to use these traces. I think these will be released after DPC. And we are very, very interested in supporting the community in using these traces to the best of our ability. So please reach out if you have any feedback. I'm happy to work with folks to refine the traces if needed, or any support we can provide. And mostly we're just sort of really curious on what you all find from these traces. A couple of important things about the traces that might be relevant from the point of view of the competition, or for prefetching in general. The traces incorporate the notion of scheduling. So because each application has hundreds of threads, the checksum traces that are there, each trace actually mimics a schedule of multiple threads on a single core. So threads are scheduled across a variable number of cores. The number of cores depends on how many number of cores is this application use in Google's production fleet. And so if you simulate one trace, you see many different threads context switching on one core. And I mean, I think it's an open question on how does that affect prefetching, and are there any interesting things to do there? The traces are also front-end bound. So I think, at least from the point of view of the competition, we probably need to unblock the front end. So maybe more front-end prefetchers to expose the data bottleneck. Yeah, so I think these two things might, I caught up on the beginning of the workshop, and we weren't seeing huge improvements on Google traces. And so moving forward, I think paying attention to these two things might sort of unlock more interesting work on the Google traces. So that's on the workload side. The second lesson that I sort of had from working at Google for so long is many core systems actually do not respond as well to prefetchers as we are sometimes led to believe when we do single core simulations. In Google's fleet, it is common for hundreds of cores running tens of workloads, all contending for shared resources. There is no single core system, right? And so when you're running hundreds of cores together, the trade-off between coverage and accuracy becomes much, much more important. Because if your machine is highly utilized, if you're using all those 100 cores to run different applications, there's a huge amount of contention on shared cache, shared memory bandwidth. And there isn't really that much room for prefetchers to be wasteful. So again, a big shout out to the DPC4 organizer for prioritizing low bandwidth configurations. This is absolutely a step in the right direction. I do think a lot of single core simulation work tends to mislead us if we are like looking to make real progress on large systems, because with prefetchers, it is relatively easier to get performance on single core systems. But having that scale to a large multi-core system is hard in a way that you don't sacrifice all the coverage that you were getting from the prefetcher. So we had this paper in ASPLOS a couple of years ago where we discussed this issue. And this chart here on the left is sort of showing you that over the years, these are looking at multiple server SoCs in Google's fleet, the numbers of cores per socket keeps increasing, but the memory bandwidth that you are providing per core kind of remains flat. At the same time, if we look at several commercial CPUs, we see that the prefetch traffic overhead keeps increasing. And it can be almost 50% of total traffic. And this is not tenable because as you can see, I mean, you have the same amount of memory bandwidth per core, but your prefetchers are just trying to eat up more of it. The logical conclusion of this is it just forces us to make bad choices. Like we have two really bad choices. I either need to provision more memory bandwidth per core to get the performance benefit that the prefetcher is providing. And this is very costly. And so for an SoC architect, this is a huge dent on cost. Or we have to disable prefetchers to reduce our bandwidth requirements, which comes at the cost of performance. And so what the latter is unfortunately what we had to do. This was sort of my first project at Google, where at high utilization, where the machine was highly utilized, that means all the cores were running some applications, we had to disable prefetchers because of the very high latency penalty. So on the right, the chart that you're seeing here is showing a loaded latency curve. X-axis is memory bandwidth utilization. Y-axis is the latency to go to memory. And what we found was that if we disabled prefetchers, we suddenly saw a huge benefit, I think about a 10% reduction in memory latency at load, which was a huge performance boost to all applications. So we got a 10% performance win from just disabling prefetchers at high utilization. And this was a huge amount of performance at the scale of Google. And while this was a very exciting project because of numbers, it was also bittersweet for me because as someone who worked on prefetching in academia and industry for a long time, I mean, the best solution was to disable prefetchers, which is not very satisfying. But this did come at a cost, right? So prefetchers help us improve our cache hit rates. And when we disabled prefetcher, even though we saw huge latency benefits, we did see an MPKI regression. There was a 20% MPKI regression, especially in key data center tax functions. So this chart is showing some important data center tax functions, and all of them regressed. They all lost performance. And so this, to me, this said that there is room to prefetch. It's not that the applications are not prefetch friendly. They are prefetch friendly. It's just that there's a fine-grained polarity for prefetching, and that we cannot be as wasteful or willy-nilly prefetch things. We cannot have so much waste because that does add a latency penalty when the machine is loaded. So in our AskPLOS paper, we had the solution of hardware-software co-design. It's called Limoncello, where we dynamically disabled hardware prefetchers to reduce memory latency. And then we had targeted software prefetch insertions in a data center tax code to improve the cache hit rate. And the goal here was to try and get the best of both worlds. And overall, like I said, this was helped us get all the performance or a lot of performance from prefetching. But I will tell you that inserting these software prefetchers is hard and it is painful. And it was a painful project. And the thing with software prefetchers is you have to place them at the right location. And if your machine utilization changes, if the workload changes, it's just really hard to get it right and then also maintain it. Which brings me to my third lesson, is that in this whole experience, what I found was that the hardware-software interface that we have for prefetching is extremely inexpressive. As a person who cannot change the hardware, I only have two interfaces to program hardware prefetchers. I can either disable them completely or disable a subset of them. This obviously comes at the cost of coverage, like we just saw. Or I have this other option of trying to do everything in software, prefetch everything in software. And then this is hard because the software has no knowledge of hardware contention. It has no knowledge of timeliness. It has no knowledge of what is in the cache. I really can't do anything else. Fundamentally, broadly, the problem is as we design prefetchers, we rely on the hardware to do too much. We over-engineer solutions to a few benchmarks in simulation environments, and that makes it really, really challenging to adapt to the diversity of workloads and just the diversity of utilization and contention scenarios that we see in the data center. So the flip question is then, well, should we do everything in software? Should we only be doing software prefetching? And you will find folks at Google who will say yes to that. But it is difficult to maintain software prefetchers. It is difficult to insert software prefetchers because having them adapt to varying system conditions due to multi-tenancy, it's just hard. And the reason I'm harping on software interfaces is if we go back to our design paradigm, again, the way we do things is we sort of identify a few things, a few workloads that we think are golden, and then we optimize everything for that. Given the scale of a large data center fleet that has millions of machines, thousands of workloads, the workloads are always evolving. There is no good common case to bake in hardware. And so that sort of like leads to my last lesson on heterogeneity in the data center. Data centers have a lot of heterogeneity. There are many different platforms with different system balance points. You have workloads that are constantly evolving. And then if you're building hardware today, you're probably building it, it'll be deployed 5 to 6 years from now. Who knows what workloads people are running then? The software stack, such as the scheduler, which schedules all these threads onto cores, which schedules different machines, different workloads onto different machines, decides which workloads are co-located, that evolves. And again, there are many different utilization scenarios. There are different products. For example, you may send a high utilization. Your machine might be highly utilized when you want to optimize for cost, or it may have low utilization when you're optimizing for performance. So trying to identify and optimize for a common case leaves a lot on the table. It leaves a lot of performance on the table. And so, at least in my mind, the right approach for data center prefetching is software defined. What if I could choose the best prefetcher or the best prefetcher setting for every workload that I had in the data center? We have thousands of workloads, or even every workload phase. We did see that there's a fine-grained polarity to prefetching, and why can I not choose the best solution for every mini phase that I have in my application? Software stacks at data center companies are extremely complex and sophisticated. Profile-guided optimization is extremely common. It is fact of life. And as we have LLM-based agents, all these things will likely get much easier or automated. So at least in my experience, in the hardware prefetching community, we are a little bit averse to the idea of changing the hardware-software interface because we think the hardware can do everything. And yes, it can probably do everything for the workloads we have evaluated in our simulators. But the real world is messy and the real world evolves. And like I said, there is no one common case that you can just burn in hardware. The notion of software-defined prefetching can adapt to diversity of workloads that exist today. It makes us more resilient to workload changes that might happen in the future. The real challenge really then is defining good hardware-software interfaces, which, as I discussed, as of today is really, really lacking. In my mind, a good division of responsibility between software and hardware, and this is one thought, there might be other thoughts that folks have, is that the software is really good at figuring out which part of the code is actually prefetchable. You could have profile-guided optimization, static analysis, or even developer hints. People have a good sense for like, hey, this part of my code should be easily prefetchable. And that can ensure high accuracy because we're not wasting our effort prefetching in parts of your application that are just random or see a lot of data churn. And then the hardware is really good at sort of looking at the dynamic state of the system and detecting and initiating prefetcher, which can ensure high coverage. So a final note on competitions, I think it's a great way to bring the community together, evaluate different solutions in a common framework. If I had a wish list for DPC5, it would be obviously we would like to continue our work with Google Traces, but also provide more incentive for low bandwidth wins. Any win in the high bandwidth setting is meaningless, at least for a data center, from a data center perspective, because the low bandwidth scenario is the common scenario. I would love to see more cross-cutting optimizations, for example, prefetchers coordinating. And I realize this is hard, but if there is a way to encourage the community to think about co-design and build hardware and software together, I think that would be an amazing outcome. So in conclusion, prefetching is very, very important at scale due to the large memory bottleneck that we have. Wasteful prefetching is a huge liability, and in the pursuit of sort of minor spec gains, this has unfortunately become very prevalent to just have a lot of wasteful prefetchers that are you're using 20% memory bandwidth for 1% spec performance, which probably in the data center translates to 0% performance. The right prefetching for data centers, in my opinion, is software defined, but we do need right hardware software interfaces to enable this paradigm shift. So with that, that's all I have, and I am happy to take questions for however much time that we have left.
Thank you very much, Akanksha. So let's. Okay, we have question.
Hi, Akanksha. Thanks a lot for the talk. It's very insightful. You mentioned about the workloads, the hardware software co-design, and the limited bandwidth cases you want to see in DPC5. What about multi-tenancy? You mentioned that. Can you, coming from a data center company, drive useful scenarios for multi-tenancy? I know there's a lot. but is there any particular ones, or, in academia, you see a lot of studies randomly mixing workloads or workloads that have high bandwidth, low bandwidth requirements. Are these enough? Can you help define some of those?
I think that's a great point, and I think that's where we are headed. There was a lot of work we had to do in just figuring out the scheduling and the simulation for a single workload. But yes, how we co-locate these different workloads in a way that we can actually simulate them, because we're not obviously going to simulate a 100-core system. So certainly, yes, I don't think we have anything right now, but it's on the cards, and I'll take a note and I'll do my best to sort of provide some methodological guidance on that in the future, in the near future, hopefully. Thank you for the question. Yeah.
Hi, thanks. Try to get into the picture. Thanks for the talk. It was very interesting, but I wanted to also add to the multi-tenancy question. Sometimes multi-tenancy exists within a single workload, even without the multiple cores, right? Because in data centers, you pass through so many levels of encapsulations and virtualizations and other aspects or library calls that are often not captured when we currently run our simplex, because we look at an application, maybe a few additional. So how would you go about capturing this diversity of behavior, right?
Excellent point. And I will say these traces are a start. They're not perfect. For example, they do not capture a lot of kernel behavior or virtualization overheads that you may sometimes have. But again, in the interest of, and let me also point out, like, getting these traces is hard. Getting these traces out of a production workload is extremely hard, and they're not perfect. But again, I think the traces that we have can add a lot of value, and we have colleagues who are working on this, and the traces that we release are sort of one step behind what we have internally at Google. And so there are things in the pipeline, and as and when they're ready, we will do our best to release them to the public. But in the case of these traces, I think the idea was to let's release something that we have and not wait for them to be perfect. And hopefully we can still learn a lot of insights from these. But like, for example, lack of kernel cycles, which is a significant portion of cycles spent in the data center, and virtualization is a limitation that we have in these traces right now.
One question, maybe, due to the interest of time. I'm sorry.
Thanks. All right. So you mentioned that the traces we have are somewhat limited and you'd like to make them better. Is there any chance that a future version of these traces would include actual memory values or the values being loaded into memory, into the cache? I'm asking because some memory access patterns are very easy to prefetch if you have that information and almost impossible otherwise.
I think values is going to be challenging just because of IP issues. So yeah, I think value, I think it's very unlikely that those would be released.
Okay, one quick question and that's it.
Thanks for the talk. One question is, do you envision these software-hardware interfaces to be used in any other application with respect to hardware? Like you mentioned hardware prefetching. Do you see them being useful for other domains like cache replacement policies or something else?
Absolutely. I mean, the same principles apply just because we have so much heterogeneity. Yeah, I mean, the simple answer is yes. I think defining the right interfaces for all the microarchitectural optimizations we do would be an immense performance boost in the data center. And the simplest thing is if I could just choose, for example, the right hyperparameter thing for every application I have, I think that itself would be a performance boost. But then what if you could go further and actually design a replacement policy or a branch predictor for every application? If an interface enabled that seamlessly, I think there's a huge performance opportunity there.
For the insightful talk, let's give her a big hand again. Thank you, Akanksha.
Thank you so much for having me.
Okay, so we are going to have the next talk. I think we're running a bit late, but that's fine. So the next talk is going to be from Simranjit, I guess. So Simranjit is going to present pushing the limits of the Berti prefetcher. let me set up the stage for him.
Hi, I'm Simranjit from the University of Murcia, and today I present this workload with Agustin Navarro and Alberto Ros. So in this work, we noticed that we have a fairly strong baseline in the DPC4 championship, and which is composed by the Berti at L1 and PTA at L2. As many of you noticed, there are two versions of Berti. There is a one presented at the last championship, the DPC3 and another newer one, which has some improvements that has been presented at the Micro 22. So we moved the baseline to the Micro 22, which has key advantage. It has a simplified design, which also does translate to a lower storage budget at init, so we have more room to add. Then it uses virtual addresses, which allows cross prefetching. It is delta per IP per instruction pointer, and it also tries to not only answer what to prefetch, but also when to prefetch and where to prefetch, if L1 or L2. So what are the key concepts that at a very high level Berti is trying to introduce? Well, it's a local delta prefetcher, and the concept of delta contrasts the concept of strides. The stride is the difference between two consecutive addresses. In this case, we have a stride of 3 because it's 15 minus 12. Then the delta is the difference between one access and any another access on a stream. In this case, we see a delta of +8, +5, +3 for the access 15. So this turns out it has nice properties because let's think even in a very simple pattern, in a stream pattern, in an S line, +1, +1, +1, in an out of order engine, it can change. It can become +2, -1, +3. So it adds some robustness to the concept of stride. It also adds, it can allow us to be more timely, because if you're prefetching +3 at access 12, you might be too late. So then Berti expands on these ideas, and in the paper are described how it uses it to get the performance. So our approach is a deep analysis in first place of Berti. So where we can improve an already good, we are trying to push the limit of an already good prefetcher. Then we make some changes to PTA, and we propose adaptive next line at LLC. So let's start with Berti. And we noticed, as many of you, that there is a huge gap between what Berti wants to prefetch and what's end up being prefetched. And it turns out it's prefetching a lot of data which is already in the cache. There is a lot of repetition. And don't get me wrong, this is not by itself useless, because you are saying to the cache, hey, you have this data, don't evict it because I think it will be used soon. But more often than not, you are choosing between bringing new lines or making these hints. So because you use a prefetch queue slot, you use a port slot. If this is going to L2, you are using another queue slot and another port. So we
try to figure out how we can filter. And we tried a bunch of different kind of filters, and we propose a region-based bitmap filter. So we are having a region tag. In our case, it's just the page, no aliasing, the whole page, and a bitmap which stores which offsets of the region we have. In this case, the 64 offsets possible on one page. It can change the granularity, that's configurable. And in each access or prefetch, we set that bit. And if it's already set, we will skip it. And in L1D eviction, we will clear that bit. So this turns out it also has a nice property because when we are prefetching to L2, we usually have less confidence rather than when we are prefetching to L1. So we can make mistakes. But these mistakes will never be promoted to L1, so we will never see an L1D eviction. So even if there is a L2 eviction, we will keep suppressing this bit, this arrest line until there is a eviction by capacity of the filter. The filter is a big one because, and it's associative, but you can make a smaller filter. Each line entry is taking like 64 possible address, and there is some locality, so it's exploiting it. So you can make it smaller and don't lose much of the performance, but we aim to use the full storage of the DPC4 computation. The second inefficiency is we ask Berti works per instruction pointer. It's the data per instruction pointer, but we find out the same instruction can miss some context, and it doesn't only measure the instruction pointer, but how you got there. So this allows us to filter some noise and build the confidence we need to prefetch earlier. So we track the last 4 instruction pointers, we hash them into a pass signature, and we query the delta table and the history table with both of them. Then we merge the predictions, and it turns being very effective for AI and ML workloads. We get a huge bump there. So it's also using the same history table. We don't span it more, and we don't span the delta table to this. So it's using the same data structures, and it adds the storage for allocating the portion of IPs we want to use. So this, as we moved with this is a subset of, well, this is the training data. So the data, the final data can be lower, and I expect to be lower. But using the Berti of the micro alone, we are like minus 4.1% over the DPC4 baseline with PITIA and Berti from DPC3. Adding the filter, we get to 1.6, and adding the missing context information with the IP path, we get to 2.3, and we further improve up to 9.6, adding Vertigo with PITIA. This is in a full boundary configuration. Then we move to PITIA, and PITIA is really it's a full prefetcher. It takes another angle to the same problem, so it complements well to Berti, and it's just a reinforcement learning approach. So it has a series of input, then there is a reward system, and then it's a output of what we want to prefetch. And you can tweak the rewards to make it maybe more aggressive or maybe more bandwidth aware or whatever. But what I found interesting of PITIA is there is a deep analysis on different inputs that PITIA can take. It can take maybe the instruction pointer, the page, the offset, and in the default DPC4 configuration, it is using the instruction pointer or the instruction pointer with the delta. That means if any of these two features, as it's called in the paper, boards to prefetch something, it will prefetch that something. So what we notice, it works on average really good, but in some workloads we can improve. We can maybe select not prefetching at all at L2, or maybe just taking the words from the instruction pointer or the instruction pointer with the delta and ignore the other, and or using IP and IP delta, which is more restrictive. Both has to go to prefetch some address to end up being prefetched. So we inspired us about the catch replacement style of set dwelling like as proposed by Kershi, and we assign each set to one candidate, one format, one feature. So candidate one set is just no prefetching at all. The second is just using the instruction pointer. The next is using the instruction point delta. So we divide the whole catch into different configurations, and we track the miss rate of each of these configurations. So, and then of the winner, we will pick the best miss rate we have if it's at least 4% better than no prefetch, because no prefetch asserts no overhead to the memory system because we are not prefetching. So this policy is allow us to adapt to some workloads, but also the same workload and a different configuration, because it might change the behave in a full bundle configuration or a limited configuration. Adding this moves in the to a 10.2% of performance over the baseline. I repeat, this is on the training set of traces. So, and then at last we move to LLC, and we propose an adaptive nestline. We observed that for some workloads, doing a nestline prefetching does work, but for some it doesn't. So what we do in each access, we have a sample catch, and we will track the nestline prefetch on that sample catch, and we will only prefetch if the prefetching of nestline is enabled. On a demand hit on the sample catch, we will update the useful counter, and if it's late, we will update adding 0.5 to the useful counter. And if there is an unused eviction, that means a prefetch that never sees a demand, we will update the useless counter. And after a number of evictions, we separate and see if useful is by higher than useless. We will use the nestline prefetching. There is a huge store, like 209 kilobyte, that because we are using the whole storage budget. But we have tried another version of Aneline with only 10 bytes in a slightly different approach, and that gets similar results. So this adds to up to 10.4% of performance, and this is the performance in limited configuration, and you get 4.5 in limited configuration. As you see, we are not getting that much in Google, so we have to analyze it in future work. That's why, because there is a huge amount of Google traces, we expect a lower performance in the whole in the final results. But in conclusion, what we are doing in Vertigo is eliminating as best we can the do not requests, and we are adding a context, the IP path context to Berti. We are doing an online fine tuning at PIDIA, and we are proposing an adaptive nestline at LLC. Thank you for hearing me here, and thanks the organizers to make this possible.
Question for Simranjit. I have one question. So the set dwelling for Pythia, unless the audience doesn't have. Okay. So the set dwelling for Pythia, so you, I think, evaluate different features for different sets, right? So
yes, right.
So how the evaluation works, like if you go back to that side, yeah.
Yes.
So you're evaluating all of these features, I believe,
yes,
based on different cache sets. So how does this like work?
Well, there is different format to implement this set dwelling. We are evaluating for 10 million of instructions. What we are evaluating, how many misses and how many access we get for each configuration. And we are selecting the best ratio if it's 4% better than the no prefetch. But we also tried to use a subset, and it also works well. And what we observed that in the DPC4, at least on the training set, there was not a phase change, so we don't made it dynamic really. So it's a static decision we made we run it for 10 million instructions, we see the misratios, we select the winner. That's how we're doing here.
That's a cool idea. Okay.
I just want to add on this. So basically, you are using some sampler sets, or you use globally a configuration of PCL, let's say with the IP feature. Then you run 10 million, you check the MPKI, then you try another feature. That's what you're doing.
Let me explain. First, I use it as sample catch. Sorry, a subset of sets, and we run the
sampler
default
sets
configuration. But then I changed it. The whole catch is divided because it was more simple, and I implemented it this way for the DPC4. What we are doing is dividing the whole catch. We assign each set to one configuration. So each set is one configuration, and then after 10 million, we are selecting which has the best.
Which set has
which configuration has the
Running all of these.
Yes, we are running for 10 million of instruction. We are running all the configurations, and then after 10 million, we are measuring for yes.
But since one set assigned to one configuration, since you are doing prefetching, then the prefetch might end up in a set assigned to another configuration. No?
Let me think about it. It's the we are just.
Do you tag?
We are using this.
No, it's just a comment. We can take it offline. We can discuss. Great work.
Okay, so let's thank the speaker once more. For the next presentation, we would have Augustine presenting the Entangling Data Prefetcher. Augustine is from University of Zaragoza. Let's set it up.
Hello, everybody. I'm Agustin, and I'm going to present the Entangling Data Prefetcher that I did with Simrajit and Alberto Ross from University of Murcia and Biswabanda Panda from the Indian Institute of Technology of Mumbai. Since Simrajit already explained Berti, I'm going to jump into the first question that we made when we start developing a new prefetcher. That is, I thought something that I don't know.
No, it's fine.
Sure. Oh, okay.
Let me see.
Okay.
Some reason it mark is still there. So let's just close it. Sorry.
No, don't worry. It's my fault. Okay. Thank you. Sorry for the issue. So the first question that we made is, where does Berti fail? In this case, the state-of-the-art prefetcher. And okay. And we take this graph from the Micro 2022 paper that saw all the benchmark from the spec CPU and the speed up. And we saw that in Cactus, Berti achieved 0% of performance improvement, and the other prefetcher achieved some performance improvement. So we made the question that why is Berti fail? Why can Berti not cover Cactus? One of the reasons is that because there is too many P's in this kind of benchmark, but you can solve it just increasing the size of Berti. The other reason is that Cactus has what we call very long time distance stride. The figure that appears is from the TSKIT paper from the third data prefetching championship, as so in the axis E the time, and in the axis X the address. The address that are in the same vertical line is address from the same IP, and as you can see in the B, between accesses from the same IP there is around 2,000 accesses. That means, and this is an example, that if we have this timeline and we have a simple +2 straight pattern, every 2 cycles, the IP access the address, for example, +0, and then evict the address +0. Accesses the address +2, evict the address +2. What is happening is that Berti can learn that pattern. Berti can learn that he has to prefetch with straight +2 or with delta +2. And when there is a missing address +6, it will say, okay, I have to prefetch address +8. I issue the address +8. I fill the address +8. I evict address +6. I evict address +8. And then the CPU will request address +8 that it will be a miss. So Berti can learn the pattern. The problem is that Berti cannot issue the prefetch request in a timely way. So we have this issue, and we have a paper that already explained this. That is TSKIT. And TSKIT is able to capture long distance stride and zero stride patterns. And the key thing of TSKIT is that the IP that uses and learns stride patterns can be different from the one that triggers the stride, the prefetch request. That means that if you have a +2 pattern, instead of being the same IP, the one that trigger the prefetch request can be another one that will be more timely, another IP. The advantage is that it covers the very long time distance and zero stride, and no, I want to say, not so many prefetchers can do that. And other thing is that it's built on the top of IP stride. The problem is that it inherits all the issue of an IP stride prefetcher. That is already known. So, is this important? So we analyze in the spec CPU the memory pattern that happen. More than 50% are irregular, 32 are constant, like for example, +1 straight pattern, 7% are complex, and around 5% are zero. This is from the L1D cache. So this is important. It's an important problem because it's only happening in Cactus. You don't have to solve it. It's not mandatory to solve it. Berti cannot cover zero and very long time distance stride. That means that it cannot cover at least the 5% of the misses that happen in the L1D in our experiments. And TSKIT cannot cover complex stride pattern. That means that it cannot cover the 7% of the pattern. So the question is, can we have a prefetcher that covers both patterns at the same time, the complex one and the very long time distant patterns? And that's what it is, yes. It's the entangling data prefetcher. The idea of having a new prefetcher is having a cover the complex patterns, cover very long distance stride and zero stride patterns, and we also try to improve the timeliness of Berti. So the entangling data prefetcher is built on top of Berti, since Berti is the state of the art. We use deltas, and we only use the timely deltas to prefetch. So the complex pattern is already covered thanks to Berti. If Berti covers the complex pattern, the entangling data prefetcher already covered it. And what happened with the long time distant patterns? We use that similar idea to TSKIT. We decouple the IP that learns the pattern with the IP that can trigger a prefetch request for that pattern. For example, this is a similar example that we have in the Cactus traces, is that we have the APA, and between the two axes of the APA, there is around 2,000 cycles. In the middle, there is a lot of IPs. So why we don't use a previous IP to trigger the prefetch request? The problem is which IP should use, because if we use the IPv, it will be a too early preference request. If we use IP8, the previous one, probably it will be a late prefetch. So if we search for the peak latency of a miss, we say, okay, this is easy. It's like choosing the timely delta. APG will be an IP that appears with sufficiently in advance to be a candidate to trigger a preference request for APA. So what will happen in the example? So if we have the same timeline, and we select the IPN as the trigger IP, what is happening is that AEDT already learned that this IP has a +2 straight pattern. And when the IPN comes in, they say, okay, I have to run a preference request for other IP with address +8. I issued the IP. I will be filled in the cache. Then the IP come and say, oh, I found the catch line, so I have a hit. And next, it will be evicted. But I already have a hit that in the other case, I will be a miss. The key idea is the ADP allow triggers the prefetch for another load. It's do an entangling pair. But we have a problem that other people are already saying in this championship, that one IP can, in the entangling data prefetcher, one IP can insert multiple requests for different IPs at the same time. This increases the issue that all the presenters already say, that it's saturated L1D structures, such as MSHR. So if you use only these kind of things, the problem is that you are not able to prefetch as much as you want because you use too many prefetch requests. So we present two solutions for this problem. One is a delay queue, and another one is a filter. Usually, in a processor, you have a read queue, in this example, with 2 slots and a prefetch queue. And under low contention, what's happening is that the prefetch request, the prefetch request and enquire request into the prefetch queue. And in the next few cycles, it's in queue, appear, and is issued to the cache. This is the normal behavior. But under high contention, and in some scenarios, the read queue is full, and the prefetch queue is also full. But the CPU is still requesting for new demands. For example, in this case, the read queue issue the address A, but the CPU already asked for the A+1 catch line. What is happening is that the prefetcher is detecting an strand and trying to enqueue the A+2. But since the prefetch queue is full, it will discard it. So if the time comes running, in the moment that the prefetch queue issue the address A+2, it will be useless because it's already asked by the CPU, and in some occasion already solved the miss. So what is our idea? Okay, we have a new queue, is a delay queue that kept renewing the request and only kept the useful one. If we have the same scenario, high contention, the delay queue, what is happening is that when the prefetch try to insert a new request into the delay queue, it discards the oldest one. You say, okay, this is oldest, I don't have a space, I discard the oldest one because the new will probably useful. And only, and the red queue is keeping solving all the issues, all the requests from the CPU, and only when there is enough space in the prefetch queue, and I believe that the prefetcher believes that it will be able to issue the request to the cache, it enqueue the request into the prefetch queue and issue the request. Maybe it will not cover all the cases, but it will cover more cases that only inserting requests in the prefetch queue. The second improvement that we made is a filter that potentially rejects not useful requests. Since Berti issue a lot of duplicate requests, this also happens in Entangling data prefetcher. So we propose a Bloom filter that works like this. It's like on every memory axis, including a prefetch, when a prefetch issue a new request, an entry, that's entry selected by the address, is set to 1. If the prefetch wants to issue a new request, it will access the filter, and if the entry is equal to 1, it discards. It will say, I recently see this catch line, so I completely discard this one. Otherwise, it means that the entry is equal to 0. I don't see the catch line, so I will issue the prefetch request. And when the catch evict a line, the entry will be set to 0. So this way we can clean the filter and issue more prefetchers. Okay, in what we do in L2, we include PITIA. This is because PITIA detects some kind of pattern that are not detected by AEDT, and even with all the measure, when there is a burst of L1D accesses, it can still issue prefetch requests. So even if we can detect the patterns in L1D, sometimes it's good to detect the same pattern in L2. And the second mechanism that we use is a trolling mechanism in the LLC. If we see that too many cores access the LLC, our mechanism must signal to the EDP and reduce the degree. And the second thing that is that if one core is a significant portion of requests that are not demand or prefetch, it will disconnect the entangling data prefetcher for that core. That means that if, for example, see one core that most of the requests or a significant part of the requests are extraction, write backs from the lower level of catch, or, for example, translation, we believe that in that kind of cases, a prefetcher is more harmful because it's removing useful content from L1D or L2. So we say we don't prefetch for that core. What is the number that we get? This is only for the training traces. So as SimRajit said, we expect to have lower numbers, mainly because Google traces have a lot of there is a lot of number of Google traces. We get a speed over 16% of machine learning and over percent in spec CPU. This is for the full bandwidth, and this means an average of 7.1% over single core and 1.4% in multi-core. And in limited, we get a bit less than 2%. Thank you, everybody. This is everything. Any question that you have?
So I have one question. So, like conceptually speaking, are we talking about something like best offset prefetcher, but in terms of instruction to instruction correlation rather than cache line to cache line?
Yes.
Correlation. Is that the understanding correct? Like, can we think EDP like that?
When you learn patterns, it's like Berti. You learn patterns only for that IP. But you have a correlation between IPs for triggering requested. So one IP triggers the prefetch request of another IP.
Correct. So that means you're entangling two IPs.
Yes.
In a way that, let's say, Bob figures out, okay, which cache line to actually issue it for the prefetch so that it becomes timely.
Yes.
In this case, which IP would trigger it for myself to become timely. So it's like entangling the instruction the way that Bob entangles, let's say, two cache lines, something like that.
Something like this. Yes.
Okay,
Yes.
Okay. And when do you see any effect? Any other question? Okay. Maybe I'll ask it later.
So if I understand, the main concept is that you're trying to correlate an earlier PC with the prefetch request that a later PC will do, so you can save latency. And you mentioned that there is, of course, a lot of unnecessary traffic. And I assume it's because the correlation is not always very strong, right? Between, have you measured that correlation to see how much it varies across the benchmarks?
We don't measure, but we detect that in some cases you cannot just trigger one IP with one IP because it can happen because of the flow of the application that maybe doesn't appear again. With Bandits, instead of choosing only one IP, we chose 4 IPs. And since we have a high degree, we can prefetch up to 16 at for one IP. Even there are some IPs that lack of correlation, and it's just lucky that you choose that IP. In the overview, in the global picture, you always issue some prefetch requests. You don't lose so many opportunities.
Okay. Do you see out of orderness causing also messing up that correlation, the out-of-order issue from the core?
It happens sometimes that you see, for example, APA, APB, and the next time you say APB, APA, yes. But since we chose 4, usually it doesn't matter. And usually it repeats a lot. So yes, maybe half of the time you choose one, half of the time you choose the other one. But at the end, you always issue prefetch request.
Okay, thank you.
So due to the interest of time, let's thank Augustine again.
Thank you.
Yeah, our next presenter is Charles Blog from UIUC. Charles is going to present performance-driven composite prefetching with Bandits.
All right, hi. My name is Charles. I'm from UIUC. I'm going to be presenting our submission to DPC4 titled Performance-Driven Composite Prefetching with Bandits. This was done in collaboration with all of these fine folks. So this is probably going to be a slightly different talk than most of them that you've seen today. I'm going to start by talking about prefetching feedback mechanisms. So many prefetchers, including pretty much every one that we've seen today, use some sort of feedback in order to enable or disable features or tune how aggressive they're acting. As an example, Pythia and Berti both use accuracy and timeliness to determine the best offsets to use or how aggressively to act. But there's a complex relationship sometimes between these heuristics and the actual performance that we achieve. In particular, the trade-off between accuracy and coverage can often change between workloads, or as we've heard Akanksha say in her keynote, change depending on how many other things are running on the system. And individual prefetchers could use raw performance as feedback, except this is often difficult because prefetchers generally are making very fine-grained decisions about what offsets to use or how aggressively to be, either on a page or PC granularity, whereas performance is a very coarse-grained metric. Measuring the IPC of a workload typically doesn't tell you whether one particular prefetch action was correct, but instead tells you how good you're doing in general. Separately, today we're seeing a lot of systems like the Neoverse v2 here on the right, emerging with ensembles of prefetchers. The Neoverse in particular uses 8 different prefetchers ranging from SMS to stride to best offset. And this, I think, offers a very neat opportunity because it allows us to make these coarse-grained decisions about prefetching that maybe aren't available to us when we're talking about individual prefetchers. These coarse-grained decisions can include things like which prefetcher should I disable, or how aggressively should I prefetch with one of my prefetchers. And suddenly performance-driven control becomes feasible. Suddenly we can look at how well we're doing and in terms of raw IPC or some other performance-related metric, and then tune our actions based on the raw performance instead of these second-order heuristics. For our submission, we choose to do this with a reinforcement learning model called multi-armed bandits. The name multi-armed bandit comes from a gambling problem, funnily enough, where the gambler is posed with the problem of which of these one-armed bandits do you pull the arm of? Which one is going to pay out the most? Most algorithms that solve this problem generally follow a similar pattern where you try each one in turn and record how much each one is giving you as a reward, and then choose the one that's giving you the most to continue playing. There's generally some randomness or some sort of exploration bonus involved as well, so that you might occasionally choose one that's provided less, so you can maintain up-to-date estimates of how rewarding each one is. But in general, after you play each one, you'll update your estimate, and then you'll continue to play whichever one you expect might pay out the most next time. Of course, in prefetching, we're not pulling the arms of these bandits, but instead we're choosing prefetcher configurations for our ensembles. So here, each of these possible actions include some sort of configuration for our ensemble, like enable our stream prefetcher but disable our other two, or enable all stream, stride, and SMS prefetchers, something along these lines. And of course, the reward is no longer money, but is instead the IPC that we expect to receive from our system. Implementing this in hardware is fairly straightforward. We just need some method of controlling whether a prefetcher is on or off, or the degree that it's prefetching by. And we need two tables, a table that tracks how many times we've tried a particular configuration, and a table that records the average reward that we've received from these configurations. Using this, we can make informed decisions about which configurations to use from our ensemble. And the process looks very similar to what I've just described, where we choose an ARM or a configuration that we want to configure our system with. We run it for some amount of time, and we record the performance before moving on to the next time step. After we've tried each one of the configurations in our ensemble, or each one of the possible configurations that the designer has included, we then enter sort of the main phase of the algorithm, where we start choosing configurations that we've performed well in the past, with the expectation that they'll perform well again in the future. This sounds great, but as myself and some colleagues have noted in prior work, we run into a multi-core problem fairly quickly when we use a system like this. When we include these intelligent performance-driven agents in our individual cores, they tend to overcompete for resources in shared structures like the LLC or memory to a degree much beyond what an average prefetcher would. And in fact, although most prefetchers like Pythia or Bingo become less aggressive when resources become scarce, this is because they realize that they can't prefetch things in a timely manner, so they don't. Bandit tends to become more aggressive. And this is due to Bandit, each individual agent in the multi-core system, trying its best to eke out that little bit of extra performance by dominating as much of that memory bandwidth as it can, disregarding the effects on the rest of the system. So we address this with another reinforcement learning agent following the same sort of principles called Micromama, which is a central agent that lives on the NOC, and that pushes these individual agents towards better system-wide equilibria. Micromama follows a general pattern of, after each Bandit step, recording the configuration that was just run and the performance that we found that it achieves, then computing some sort of system-level performance metric that it can use as its own reward, and then sending information back to the local agents about how they should configure themselves for the next step. This information that the central agent receives is stored in a structure that we call the joint action value cache, which records the actions that each agent has played, how many times that particular set of joint actions has been seen, and how performant it seems to be on average. Then we use a Bandit-like arbiter, just like our local agents, which includes its own reward and number tables, to determine whether or not we should allow these local agents to continue operating independently, which we might do if they're not competing by a very large amount, or if we don't have any good alternatives in our cache. Or alternatively, this agent can choose to enforce a previously seen action out of the cache onto the whole system. In this way, the global agent attempts to guide the local agents towards configurations that result in high system-level performance. Now, ideally, the reward function that we give to this global agent should be the desired performance metric that we wish to optimize. In DPC4, this performance metric is the harmonic mean of core speedups divided by the performance of that same workload in the single core case running the baseline system. This is a pain to estimate at runtime, so we don't. It would require estimating things like how much slower does multi-core make this particular workload, or how much faster would this workload run, or how much slower would this workload run if we were to use Pythia instead of our ensemble of prefetchers. These questions are difficult to answer at runtime. And so we opt for a simpler reward metric for DPC4, where we simply provide this global agent with the geomean IPC of the cores in our system. We also make this a very small part of the reward that each local agent receives, so that even during periods of time when the agents are independently exploring, they're discouraged from choosing actions that have an outsized negative impact on the system as a whole. So the full prefetcher selection that we use in our submission looks like this. None of these prefetchers are modified beyond placing them in an ensemble. Berti is used as is found in the baseline, that is. And in the L2, we replace Pythia with an ensemble of 5 prefetchers: next line, stream, stride, SMS, and best offset. These 5 are controlled by our Bandit algorithm. And in the LLC, we don't place anything, since we found that Placing any of those prefetchers that came with stock champ sim at least generally reduced the performance of our system. And we come in at under budget. Also, we have that laser pointer is not very good. Also, we have a bloom filter, just like Augustine mentioned in his last talk, for much the same reason, to make sure that these prefetchers in our ensemble don't issue duplicate prefetch requests. We expose 18 possible system configurations, which we refer to as ARMs, to these local agents. These consist of on-off settings for 3 of our prefetchers, the next line SMS and best offset prefetchers, and aggressiveness controls in the form of prefetch degree for the stride and the stream. In terms of performance, we see moderate improvement over the baseline system in single core cases. Just like everybody else today, we see a massive improvement in AI ML since it benefits from very aggressive stream. And in Google, we see a reduction, likely due to suboptimal ARM selection, which I'll talk a little bit more about in a moment. Multi-core could be better. We actually didn't quite have these results by the time we submitted, so realized after the competition deadline that we had underperformed our system by a little bit. And I'll talk a little bit more about why we think this is in a second. But I would like to highlight that Micromama, the system I'm talking about, does improve the multi-core performance of Bandit in every single category for exactly the reasons that I described before. In general, this global coordination allows for better resource sharing and also allows us to prioritize workloads that actually have higher sensitivity to prefetching, whereas the Bandit agents would just generally create a lot of contention without it. So I'd like to kind of wrap this up by talking a little bit about design space exploration. Going into this competition, we had this idea that we would automate selection of all of our ARMs, and by automating the selection of all of our ARMs, essentially automate the selection of which prefetchers went into our ensemble. We tried a handful of different optimization techniques for auto-tuning this, including Bayesian optimization and evolutionary learning algorithms, but unfortunately nothing outperformed random search. We believe that this is mostly due to the highly categorical nature of this problem combined with the massive design space that we were required to explore. I hope y'all can see that. So that's a bunch of green dots. It shows the performance of this auto-tuning over time. If it looks random, that's because it is. And in the end, it was the humans who chose the ARMs to provide to Bandit, since the auto-tuning algorithm really was not able to discover anything better. I talk about this because I still believe that automating methods of selecting ARMs and selecting prefetchers in our ensemble are necessary to achieving the full potential for these multi-armed Bandit algorithms. But traditional auto-tuning algorithms are clearly not well-suited enough for this problem. This is made even worse by the long simulation times, especially in multi-core, which make iterative processes like these time-consuming, where each iteration suddenly takes days or weeks. So that's about it. I think that these performance-driven, L2 ensembles are very promising in theory, although they clearly have a ways to go in practice. But one thing that's for sure is that system-level control like Micromama is crucial for making sure that these systems perform well. I also think that the design space exploration problem here holds a lot for future research, since this is, like I said before, this is a massive design space, and nothing out there right now seems to be very good at exploring it. Thanks.
Hi, very nice talk. Why was not Pythia used as one of the ARMs in L2?
Good question. So Pythia is challenging to use as a subcomponent of Bandit because Pythia has its own learning process. If we were to disable Pythia, suddenly it wouldn't be training on that workload because it requires this reinforcement learning thing. This is different than like, a stride prefetcher or something like this, because when we disable the stride, we can still send it the accesses that are being made. We can still train the stride so that when we turn it on, it's ready to be useful. With Pythia, with the reinforcement learning process, this is a little bit trickier. And it would be cool to see how how that would work in the future, but for this competition, we weren't able to get that to work quite right.
Thank you.
Yeah.
I want to know for multi-core, if you started your training at warm-up or after the warm-up?
Yeah, so we always start training with Bandit after the warm-up's done. Otherwise, the warm-up IPC, I mean, it's like always 5. It would be useless.
Yeah.
All right. So you have a bunch of different prefetchers, and some of them, like Stride and Stream, are relatively similar.
Yep.
Is there any case where it would make sense to choose one or the other and reuse some data structures between them, so they don't have to sit there idle and be dark when we're not running?
Yeah, that's a good question. One thing that we considered, I would have to think a little bit more about Stride Stream in particular, but one thing that we considered with this is whether, so for example, let me pull back a little bit here. So you'll notice that, well, never mind. I guess we took it out. But one thing that we did consider for a little while was whether or not we could reuse storage structures between sub-prefetchers that never appeared in the same configuration together, and thereby save on storage budget. In the end, we didn't come close to the storage budget limit, so we didn't investigate that much further. But I think that that's an interesting way that more prefetchers could be inserted into the ensemble for sure.
And take one more question, I think. And then go.
Yeah, thank you for the great talk. I have one question. So right now, multi-arm bandit or micromama is completely stateless, right? You do not measure, let's say, prefetcher accuracy. You do not measure how much bandwidth you have. Would you say, given this information, you could make more informed decision rather than completely being agnostic to the current system configuration?
Yeah, so I think that that's a good question and something that I think we've asked ourselves quite a bit. A few thoughts, I suppose, on that would be context would, I think, help in cases where that context does not exhibit temporal homogeneity, which is the principle that this sort of relies on. Because if, say, high bandwidth consumption lasts for long periods of time, then training separately on the high bandwidth and low bandwidth cases does not seem very useful, simply because we'll adapt as those situations change. However, if there were quickly alternating periods, for example, of high and low bandwidth, or if there were particular PCs, let's say, where we know that our prefetchers, like all of them, are just terrible, then contexts like that, I think, would improve the performance.
Okay, so let's congratulate again with Charles. Okay, so our last and final presentation for today is from Leeor Peled, I guess I'm pronouncing correctly. So we're going to present global Berti, simultaneous streaming, and spatial prefetching.
Maybe one of you are to disable everything, but this is very bad. So eventually with this, you will not end up selecting the disabled.
Actually, we select it more often than you would think, especially in the multi-core case.
Okay, so actually, you don't need any hardware selection. Eventually, this will lead to the not prefetch because it will see that the IPC is going down.
That's the idea. I think what hurt us a lot is I didn't pause on the arms very long, but we have a lot of very high aggressiveness arms and very few low aggressiveness arms. And oh, sorry.
Okay. Hello, everyone. I'm Gil from the University of Toronto, and I'm here to present our DPC4 entry called Global Berti, Simultaneous Streaming and Spatial Prefetching. The idea here is that we can expand our prefetcher covering from the streaming patterns covered by the Micro 22 Berti that you've heard about a few times now to also cover different spatial patterns, and we can do this for almost zero additional cost. We achieved this by accessing Berti's history table vertically, reading columns where Berti only read rows. Our global Berti is up to 1.89 times faster than the DPC3 Berti without any other prefetchers, and still up to 1.49 times faster when we have PyPia at VL2. So first, I'm going to explain what's the difference between streaming and spatial, because as you saw earlier, streaming is usually classified under spatial. Well, let's consider this simple example code at the right. The code here is iterating through an array of linked lists and summing up their data, and I chose it because it includes both streaming and spatial access patterns. So here we've got an example of what I'm calling a streaming access pattern, and here in each access, this line of code is going to access a memory location, a consistent delta from the previous instance of that line. This makes its accesses predictable going far into the future. On the other hand, over here we've got a spatial access pattern. Here the list nodes are distributed randomly through memory, so we are not going to predict any of our accesses to the data without either a very expensive Markov prefetcher or a content-directed prefetcher, which you can't do in ChamSim at all. However, the accesses after the first in this pattern are a consistent delta from the first access. Prefetching for a spatial pattern like this is going to miss on the first access, but we can hide some of the miss latency for future accesses within the miss for the first access. Finally, in blue, we have a line which has both streaming and a spatial pattern. The access to the list tails is a streaming pattern, just like the heads, but we can also see that it's a consistent delta from the prior access to the heads. These dual patterns are going to happen anytime we've got multiple streaming patterns happening with the same delta and rate. There. So now, let's go over some background on how Berti works. You've seen this before, but I'm going to go into a bit more detail on some things. So Berti is using two tables to detect and to prefetch spatial patterns. There is some additional storage to calculate the fill latencies for cache misses, but we're going to skip that here. Berti uses the instruction pointer to index into a local history table that stores the cycle when the access was demanded as a timestamp. When the fill latencies become available, Berti is going to use the information in the history table to calculate timely deltas, which it stores in a delta table. And on each demand access, Berti uses the access instruction pointer and address to generate prefetch addresses from the delta table. Berti is issuing prefetches for streaming patterns by checking each load against the delta table, and this delta table maps instruction pointers to delta coverage pairs which track how often a delta is timely. The counter for each row is incremented each time that row is demanded, and when it overflows, the deltas are more likely more often than a threshold are activated for prefetching. On each demand access, Berti is checking the delta table for a row with a matching instruction pointer, and if it finds one, it's using the high coverage deltas from that row for prefetching by adding their deltas to the access address to generate prefetch addresses. Now, each timely delta is getting its own prefetch coverage counter in that row, and each time timely deltas are found, their coverage fields are incremented. Now, where do these timely deltas come from? Berti is finding them using its history table. The contents of a Berti history table are, for each instruction pointer, a FIFO queue storing address timestamp pairs. For instance, let's suppose the first access to the heads array from our code example is address 0x100 at timestamp 5. This access will be placed in the FIFO queue. And if the next access loads address 0x108 at timestamp 15, that's also going to go into the queue behind 0x100. And finally, let's say the third access loads address 0x110 at timestamp 35. So the queue now looks a bit like this. Now, let's suppose that the access on the left took 25 cycles to be filled in VL1. In that case, Berti will subtract that 25 cycle fill latency from the access timestamp to get 10 as the maximum cycle for timely prefetching. Berti will compare that maximum cycle with the timestamps of each earlier access in the FIFO, and it's going to find the middle access at cycle 15 is too late. The right access at cycle 5 is in time. If Berti had prefetched address 0x110 when address 0x100 was demanded, it would have been in time to hide all the memory latency. So, Berti is going to subtract the right address from the left address to get the timely delta for this instruction. Now, let's talk about how Berti could be a bit better. Now, while we previously showed one FIFO for the Berti history table, it's actually a collection of FIFOs, one for each instruction pointer. But this is a very abstract diagram. Laid out in an actual table, it would look a bit more like this. The contents here are the same as the previous slide, with the addition of instruction pointer tags to disambiguate aliasing instructions. New accesses are shifting in from the left, and the oldest accesses exit the FIFOs from the right. Now, whenever Berti searches for timely deltas, it's accessing one FIFO, or one row of the table, reading it horizontally. By doing so, Berti finds streaming patterns, because those deltas exist between accesses in the same row. Spatial patterns, on the other hand, appear as deltas between accesses in different rows. As a result, while Berti finds streaming patterns by reading a row horizontally, it can't find spatial patterns that cross rows. The spatial patterns are still in the table, though. If we look at just the first column of a Berti history table, we can see it forms a useful subset of a global history of all accesses. In fact, the first column of a Berti history table is storing the most recent access by each instruction pointer, just what we need to identify the spatial patterns. By accessing the first column of Berti's history table, reading vertically can allow us to find the deltas for spatial access patterns. So let's see how we design our global Berti prefetcher. The tables in global Berti look the same as Berti's from the outside. We have a history table and a delta table. The main difference is in how we access our history table. When latency information becomes available, we access the history table horizontally, just like Berti, producing a set of streaming deltas for a single instruction pointer. And on each demand access, we instead search the first column of the history table, accessing it vertically to produce one spatial delta for each instruction pointer in the first column, using the IP tags to recover those instruction pointers. Now, all of those deltas are going to go into the delta table rows for their instruction pointers, and we use them to produce prefetch addresses on each demand access if they have high coverage. This simple and naive approach is almost everything we need to prefetch spatial patterns. It's just got one major problem, which is that there are too many spatial deltas. Let's return to our example code and memory layout. Here, I showed a few streaming and spatial deltas, but there's actually many more than that. For instance, streaming access patterns have a valid delta for each multiple of their stride. This is a good thing. Berti takes advantage of it to find timely deltas instead of just one delta. But spatial patterns don't give the same option to choose from because we can only start prefetching from the first access. But the same delta could show up multiple times. This is not a problem if we have a consistent spatial pattern, but if there isn't one, we could saturate our coverage far too quickly from many different IPs accessing the same cache line. And what about our access to both streaming and spatial patterns? Here, we see an excessive number of deltas between the two streams. This is a problem because it can fill our delta table with redundant spatial deltas, leaving no storage for the actual useful ones and flooding our prefetch queue with completely redundant prefetches. As a result, however, when both streaming and spatial deltas are present, we need to ignore the spatial deltas. This is fine, we already have the streaming ones. Now, to limit the spatial deltas, we add some additional bits to the delta table to rate limit them. The increment bit here is added to each delta coverage pair and controls whether the coverage is allowed to increment or not. We set it on each demand axis to that delta table row and reset it whenever we increment the coverage. This enforces at most one coverage increment per demand access. Second, if a horizontal row access to the history table results in a high coverage streaming delta, we set a stream bit in that row. When the stream bit is set, we block adding spatial deltas going either to or from that instruction pointer, because if a streaming pattern is present, then any spatial patterns will also have their own streaming patterns, and streaming patterns are going to take priority over spatial ones. These additional bits, one per row and one per delta, are the entire storage overheads of our global Berti over the original Berti. Here we can see what the tables look like for measuring the storage overheads of both of the original Micro22 Berti and our global Berti. As you can see, they're almost the same. If you look very closely, there's one difference for the delta table, which is the entirety of our overheads. As a result, global Berti's overheads over Berti are pretty negligible. We oversized Berti's tables here because we had the space in DPC4, and we still are under half the limit for DPC4 capacity. Now, let's see what the evaluation looks like for global Berti. We measure using the DPC4 1-core 4-bandwidth configuration across all the public traces with the standard method 50 million warm-up, 200 million test. We are comparing to DPC3 Berti at the L1, both with and without PyThea at the L2. And what we find is that our global Berti outperforms DPC3 implementation of Berti by a pretty wide margin. In this plot, each black bar is the G-mean speedup of our global Berti over DPC3 Berti for a category of benchmark traces. The green bars represent the range of speedups, ranging from the worst to the best. First off, we can see that our largest speedup comes on spec 17 with an up to 1.89 times performance improvement. On spec traces, replacing Berti with global Berti results in a geo mean of 12% IPC improvement. Graph benchmarks also see a large improvement, with a G mean 11% speedup and no traces of a slowdown at all. AI traces see a smaller improvement, which is driven basically entirely by the llama models that see significant improvements. The other traces are a wash. The AI G mean speedup is 5%. Google's traces see a more consistent speedup, except for the Charlie workloads that have a small slowdown. The G mean for them is also 5% improvement. Overall, global Berti is outperforming DPC3 Berti by G mean of 8%, with the range going from -8% to 89% improvement. Now, of course, baseline configuration for DPC4 is not just Berti, it also has PyFia VL2. PyFia is reinforcement learning based, and the reinforcement learning agent takes the instruction pointer, some deltas, and the bandwidth utilization, and it outputs whether or not to prefetch, which delta to apply to the current address for prefetching. If a prefetch is useful, that gets fed back as a reward. As an L2 prefetcher, PyFia is limited to prefetching within a page, and it also happens to be producing at most one prefetch per memory access, just based on what actions it has. And that limits its ability to hide latency from spatial patterns that have many accesses. In this plot, we are now normalizing to a 4 DPC3 baseline with Berti at VL1 and PyFia at VL2. The first two bars in each cluster are Berti and global Berti on their own, and they show the benefits of adding PyFia to the system. While the third bar is global Berti at VL1 with PyFia at VL2. Here, the different trace categories behave a bit differently from each other. Spec 17 and Google workload see no particular change in the speed up from replacing Berti with global Berti when we add PyFia at VL2. Here, the benefits from global Berti seem to be orthogonal to the benefits from PyFia, so we are getting the same speed up from replacing Berti with global Berti, regardless of whether or not PyFia is present. On the other hand, for graph benchmark algorithms, the result is completely different. For graph algorithms, we can see first off, global Berti on its own is already outperforming both Berti and PyFia together by about 2%. However, the speedup of global Berti plus PyFia over Berti plus PyFia is only about 5%, half what it was without PyFia. For graph algorithms, global Berti and PyFia are finding about the same similar prefetches, which means that the benefit of global Berti over Berti is much smaller because PyFia was already bringing a lot of information into VL2. For AI traces, now we have something really interesting because you actually see a larger G-mean speed up from a global Berti over Berti when PyFia is present compared to without. This is driven mostly by the RWKV traces. On those traces, neither PyFia nor global Berti were providing a big speed up over Berti on their own. But when we put both of them together, suddenly we see a large speed up. Our explanation for what's happening here is that global Berti's prefetches are providing some sort of useful hint to PyFia's reinforcement learning algorithm, or alternatively, they're breaking up an access stream that was tricking it in some way. Overall, with PyFia VL2, global Berti is outperforming a Berti, DPC3 Berti, by a G-mean of 6%, ranging from -6% to 49%. So, in conclusion, by reading the first column from the per IP history table, we've enabled the Berti streaming prefetcher to also prefetch spatial patterns for almost zero additional cost. We expect that this approach is going to generalize and work for other prefetchers that use per IP history structures as well, which means that prefetchers don't need to choose between local and global histories. You can get both at once for free. Thank you for your attention. I'll now take questions.
Okay, so questions for Leeor? Any question? Okay, we have to.
Thank you. I really like the presentation. I have one question. When you access the history table, since the history table is associative or not for the global?
So in this case, it's not fully associative. It can't be. It wouldn't work like that. It's similar to the one in the micro Berti paper. Each row is each IPC indexes into a row. Each row and each entry in the row has a tag that identifies which IP it is. Rows shift down as FIFOs as you bring stuff in. When you access a row, you grab the matching tags. When you access a column, you read the tag and use that. Then you access and use the tie, associate the tie with the delta you got, and use that to find the correct row in the delta table.
Okay.
If you don't have any other questions, so let's give them clear up, give hands. Thank you, Glenn.
Oh, oops.
Okay, so that brings us to the conclusion that hopefully we all are waiting. Let me pull it up. Right. Okay, so thank you everyone for sticking to us till the end. I hope you all saw new ideas on prefetching, and hopefully this is going to, stay in the community for some time, churn out, dissect through the solutions. By the way, all of the codes are online, so I'm going to go through all the resources where you can find the codes. If all the competitors, if you want to update the code, just send it to us, then we can also update it. Unfortunately, we cannot use the updated version for the evaluation yet, but yeah, this is just for the posterity. Okay, so with that said, so let's just give first a brief round of. Okay, my animation seems to be broken, and it's still broken. Why? Yes, maybe. Okay. So now we have. So before go. Okay. Nice. Sometimes the top half comes in, sometimes the bottom half comes in. Let's try it once more. Okay. Let's not touch anything. Okay, so we have one more step. Let's see. Is it correct? Okay. So before going into the evaluation, so let me just quickly reiterate what we have evaluated with, and then this is literally a gigantic amount of effort that we took. So we are going to see evaluations across 610 single code traces. So this is what roughly the distribution looks like. A good amount of traces are coming from Google workloads, and these are going to be all released open source to for the community to keep churning on in the future. So a good amount of also workloads are coming from AI/ML workloads. So, and we kind of sweep through the entirety of this like the workload space. So all of those workloads, I need to mention it here that they are running on CPU-based inference with CPU-optimized libraries. Like for example, GGML, all of them or most of them are actually implemented with GGML. So that already kind of gives you the most optimized implementation out there. So that's what the distribution looks like for the AI/ML workloads, and then we have 359, almost 360 workload traces from Google. So these are unfortunately just the name, which is a kind of synthetic name. We don't have much of the exposure inside what's going on, but we have also tried and tested what the behavior looks like, and then the traces with the same name tag seem to have similar kind of behavior, whatever if a prefetcher works well for that one trace, then it's going to work well, for all the other traces on the same category. So, but then I would leave it up to you to keep churning on in the future. So that's what the single core performance targets are, and the multi-core performance targets are coming from 484 random 4-core trace mixes. We're also going to release the scripts that we use to randomize these things, so to be completely fair. Just a quick notation. So we actually tried to go for 500 random traces. We ended up with 484 because many of the workloads, some of the evaluation, like computing prefetchers, for some of the traces are taking too long of a time to even simulate. So we had to exclude that from the entirety of the evaluations to stay fair. So we ended up kind of with almost in the same distribution. So AIML workloads are, so all of these 4 categories essentially showing that you have 4 traces, not the same trace, but 4 traces coming from the same category running in each core. And then the cross mix is essentially saying that you pick one trace from each category and then you run it together. So that's kind of giving you the crossbreed kind of expectations. We could have done even much better mixes, but yeah, I hope that this is going to be fairly representative of what you can expect from these implementations. So just to reiterate, this is what the baseline looked like. So we had Berti at the L1D and PTA at L2 as the baseline. So that already provided 15% performance improvement in the full bandwidth configuration and 6.1% performance in limited bandwidth single core configuration. Why? Because we kind of swept through a lot of combinations. I think one of the competitors, they also attested this fact that they have also done this thing almost parallelly with us, and they kind of came up to the same conclusion that out of all of these configurations, that we found out that this is going to be fairly representative one to start with. Okay, so the scoring rubric looked like this. So every submission is evaluated in 3 system configurations to receive 3 individual scores. The full bandwidth score is coming from the non-weighted geomean speedup across all 600 traces in single core with 4800 MTPS memory bandwidth. The limited bandwidth score coming from non-weighted geomean speedup across all single core traces with 800 MTPS DRAM bandwidth. So that's like 1/6 of the full bandwidth configuration. And then you have the multi-core score, which is essentially coming from non-weighted geomean of the harmonic speedup ratio. So you compute the harmonic speedup for the baseline, you compute the harmonic speedup with the submission. I know we had some issues regarding fixing the actual metric. So thank you for sticking to us. And yeah, so that's what we are using for this part of the championship. All the definitions of the scoring rubric is online on the GitHub repository, so you can take a look at that. So overall score is essentially the non-weighted geomean of all 3 individual scores: the full bandwidth score, limited bandwidth score, and the MC score. Now the winners that we are going to see, for the sake of the ranking, we are only going to see the ranking based on the overall score. The fact that you have presented over here already means that some part of the prefetcher is already providing performance benefit, even if it's not providing the performance benefit on the overall score. But for the sake of the winner announcement, we are going to stick to objective scoring metric. So everything, as I said, all the resources regarding the traces we are going to upload in Google Drive or Google Cloud, and then we are going to link it from the GitHub repository. But if you want any resource for the that used in the course of this championship, you can find it on this GitHub repository, and that's that. So now for a surprise announcement. So we have a monetary reward. So thanks to our sponsors. And so we have the first place reward for, so these are the amounts. So that's something for the appreciation. Okay, so with that said, I would invite Onur to probably come here and have the award presented to the winners.
I'll just say, thanks for coming, and I should congratulate really Rahul because he really put a lot of effort into this, and he was very methodical and very, very fair, I would say. And everything is going to be out in the open. So people can use the code, people can improve it. But let's thank Rahul before we present the awards. And also Konstantinos, who helped Rahul very closely, but he couldn't be here right now. Also Zenron, he also helped a lot, yes, even though he's not an organizer. So. Okay, you go ahead.
Okay.
I'll take pictures. Okay.
Okay, so let's say we have joint third place winners. So the first third place winner is SPPAM, signature pattern prediction and access map prefetcher from McCoy, Lee, Paul, and Savros from Texas A&M. McCoy.
You can stand in between.
You can stand in between them.
Here you go.
Are we done? Okay. Thanks. Congratulations, McCoy. Okay, so the second joint third place goes to the Entangling Data Prefetcher by Augustine here, Simranjit, Biswa, and Alberto. I would invite all of her to come here. Hold it. Are we getting it? Thanks a lot. Okay, now the second place goes to Global Berti, simultaneous streaming and spatial prefetching by Leeor and Mark from University of Toronto. Right? And the final announcement for the winner of the championship. And that goes to Pushing the Limits of Berti Prefetcher by Simranjit, Augustine, and Alberto Ross from University of Murcia and University of Zaragoza. So congratulations. Yes. You guys are coming up again. Okay. Thanks. Yes. Again. Okay, so I'll go with it. Okay, so now let's quickly go through the evaluation results. So I would be using this for the scope of the presentation for the rest of this presentation. So these are the name of the abbreviations that I'm going to use, and these are the papers that they associated with. So this is what the overall score looks like. So on average, we are seeing, let's say, 6 submissions. They are consistently not consistently, like where they beat in the overall score from the baseline. So couple of observations that comes into the picture that Berti Go is generally the best consistently across all the 3 scores. So that's one observation that we are seeing. The second observation that we see is that across all the 3 scores on the x-axis, so higher is better, and in generally Berti Go, gBerti, and EDP are the ones that consistently outperform the baseline in all three configurations. So that's one another observation. And then another good point that we have also observed that SPAM is probably the only prefetcher that improves performance when you throttle the bandwidth. So that's also another good observations to look for. Okay, so now if we go into a bit more detail to the full bandwidth score, so this is what I'm showing over here on the x-axis, all the workload categories. Y-axis we have the full bandwidth score, and higher is better. So as multiple competitors have also pointed out that AIML is the workload category that probably gets most benefit out of prefetching, and Google is probably still the workload category that we can work with, and there is a lot to have over here. Now, if I look into the full bandwidth scores with the normalized DRAM request, so on the top side you are seeing the full bandwidth score. On the bottom half you are seeing the normalized DRAM request. So in this case, the lower is better, right? So if we look into this chart, you can see that all of these prefetchers, Emender, SPAM, EDP, sBerti, and Berti, they consistently reduce the number of DRAM requests going to the main memory as compared to the baseline. So that's one feature that we saw. And so if we kind of normalize the scores based on the unit DRAM request, so it's basically the scores divided by how much memory increase that you're seeing. So the higher number not only denotes that you have better performance, but probably you're giving that same performance at lower number of DRAM requests. So there you can see like Emender, SPAM, EDP, sBerti, and Berti, all of them provide the best bang for the buck. If we have to go for the top three, so in this case, Emender, SPAM, and Berti gives you the best bang for the buck in this case. Okay, so that's one thing. And then if we compare against the full bandwidth to the limit bandwidth score, so this is what it looks like. So one thing, one pattern that emerged into this is that even though AIML workloads experience a huge speed up in full bandwidth, they're the one that actually thrashes a lot if you limit the bandwidth. So something that we need to keep in mind for the in the future to use these traces and to extract the most benefit out of it. And then this is what the multi-core score looks like. No doubt that Google workloads are still something that we need to work on. Graph is something that consistently all the prefetchers are performing or not matching the baseline performance. So this is some category that we can still work on. So all of these like trace mixes, which traces are combined to get these numbers, everything is online. So please feel free to check it out and then try to let's say reproduce or improve upon. If you have any questions, definitely we'll be happy to help. Okay, so just to conclude everything, so we saw 8 prefetching proposals. All of them are pushing the limits of state of the art in various system configurations. It's not that overall scores low doesn't mean that they are bad. So they are actually improving probably in one configuration or the other. So this is a good time for the community to start dissecting on the solutions, maybe fine tune it, try to look for avenues to improve upon further. Another highlight that we can take away that these 482 new ChamSim traces that has not been developed before, this is all now open to the public. Community can make best use of it and try to see how it seems fit. So hopefully this would be useful for the posterity. Okay, so now for some ideas for the next DPC, and we are kind of all ears for this idea. So one thing that has repeatedly come up, thankfully, during the course of this workshop proceedings, and we have also started thinking along that line, is that how we can use the hardware-software co-design prefetcher as a means to expose for the next championship. So maybe this is a good time to take a step back and just not only think the prefetching as a black box problem with just a raw memory address prediction, but maybe with some rich set of context, software level context, and how ChamSim can be helpful in this case. So we can work on that. So given that said, there is definitely many more work to do on the system awareness. I'm glad that we are also already saw multiple solutions that have taken use of the system level feedback that we have enabled to the competitors to make best use of it. But we believe that there is even more things to be done to enable multi-core awareness, system awareness in general for these workloads. That's it. So this is another one that came up during an online discussion with Professor Todd Austin. So performance is probably not the only thing that we are chasing nowadays. By every speculation inadvertently creating some side channels. So maybe this is also a good time to think about security-aware prefetchers. So we should get the performance, but not also compromising the security. So we would think about it, how to implement these, let's say, infrastructure to verify the security, or what does even security or secure prefetcher even mean? What are the conditions that it needs to meet? But something that we can think about for the next DPC. With that said, any other suggestions if you have from the community, that would be, we were all ears. And last but not the least, I would like to acknowledge the contributions from all of the program committee members here, the invited speakers, Akanksha, Leeor, organizers, Konstantinos, Onur, as well as Zenrong for helping with the evaluation, HPCA workshop chairs, all the HPCA organizers, as well as all of you for attending this workshop. So thank you very much.
I'll make a couple of last remarks also. Thanks for attending and thanks for submitting. Hopefully in the next competition, there will be more. I'll say that maybe in the future, it'd be good to have more metrics to evaluate prefetchers, because performance is clearly important, but performance per bandwidth or bandwidth efficiency is also important. So going forward, it may be good to evaluate prefetchers with that metric. Rahul presented some results that are quite interesting, but those were not used for evaluation. The evaluation was purely on the performance metrics. I will also say that definitely we should thank Rahul again. He put a lot of work into it. And finally, I will thank our sponsors. We had two big sponsors for this. One is Huawei. Leeor gave a nice talk. And the other is Google. Google was very generous to provide 482 traces, which hopefully would be useful in future iterations of research. And we hope that some of the papers that are submitted to this will actually appear in future conferences like that happened, like it happened in the past. So there's a lot of good work that, in my opinion, this championship enabled, and hopefully people will continue this. Thank you. Have a nice reception and HPCA.
No. Oh, we're going to. Yes.